Hello, Monica ma'am.
Sorry, this
so today
is
Monica
actually
is not available.
Hello,
so
sir.
we are from Power Electronics. Hi, ma'am.
Hello,
so we are
sir.
going to discuss on Power Electronics today. So Monica is not available. Vishwanath and Vinay will be the presenter.
Okay, sir. Sir, excuse me.
Yes, tell me, ma'am.
yes.
Hello.
Hello,
Yes,
can
we
you
can
hear
hear
us, ma'am?
Sir, actually, I have installed the app. So username,
What you have
email. So
installed?
it's our username only, sir. We can enter our name, college name, email address. That's all, sir.
Which software? Which software, ma'am? PC, ma'am.
Ah, yes, sir. PC.
Registration is not required. You can skip and leave it.
What, sir?
Registration is not required, ma'am. So once you are done installation, so we'll have an option called skip in the downside.
Okay. Okay, sir. Okay, finish. Run
So,
PCM. Okay.
Correct.
yeah. Hope everyone install the PC software. If it's not, just please install the software. Meanwhile, we can go for the study part.
So when I just expand the screen and show the first slide,
Yeah.
the slide second day. So minimize your GoToMeeting.
Okay, fine.
Perfect. Just keep the screen like this. So we'll wait for some time.
Yeah, sure.
Once.
Hello, sir. Hello.
Yes, sir. Yes, sir.
Actually, I have installed this PCIM
Okay.
software. So I want to know whether by this software only electrical modeling or simulation can be done, or as well as some electronic circuits we can also simulate.
It's basically for electronics like DC-DC, DC-AC, AC-DC, and AC-AC. Apart from that, we can do we can connect the motor controls and controlling of your motors, and we have HV designs, hybrid electric vehicles, and we can do the spice analysis, thermal analysis. All this analysis can be done in this power electronics. It's basically electrical simulation software.
That means power electronics lab can be realized by this software.
Yes.
Okay, thank you.
So Vinay, in the top, I'm getting your slide shows, reviews, and everything. So could you please check that part?
Which one?
About day 2, I'm seeing some other screen. So just escape once. Okay.
Yeah, fine, right. Okay.
And open the presentation once again and start. Go to,
So is it fine now?
yes, it's perfect.
Okay. So shall I start?
Yes, you can start. So parallelly, I'll. So let me introduce about the. So
Yeah.
this one makes some questions. I'm getting some. So we are not making anyone as organizers. So kindly ignore. So don't click on any part. So mute yourself for time being. So if you have any questions, we'll kindly text in the chat window. And in the demo version, all the modules will not work. It has limitations. So we are going to show you the limitations and what are the modules we have, and accordingly can be able to work out. It's a free demo version which we have provided to you. So demo version will, it's a lifelong, so it will not expire anytime, but only the limitations are 32 elements at a time will work, and a few modules only will work. So if you want to have the full version, so let us know, or you can write us a mail. Accordingly, we can able to work out on that. So today we are going to discuss about the PWSIM software and the smart control and power force. So these are the three different software. So power electronics we can able to discuss. Today entire session is on power electronics and then control systems and power converter designing part. So in the first 2 hours, we are going to discuss on the theoretical part of the converter designing and economics of your power converters, and then the smart control part. Once you are done, we'll go with the hands-on session. So meantime, you can able to install the software which we have provided. If you didn't get the link, let us know. We'll share you in the chat window. So, so I think it's the right time to start the session. So, if, apart from that, we are going to give the feedback forms maybe after 12 o'clock. So you can fill that forms, and accordingly you can give to the Satish Kumar sir to the New Horizon College, and they'll provide you the e-certificate maybe in 7 days. So demo version is compatible. Please help us. But I have 32-bit, so it's not compatible. So yes, demo version right now which we have only 32-bit. Sorry for that. And so Kiran okay. So I will send you a link, Kiran Preet, so kindly be available. So I will try to figure it out. Okay. So yes, Vinay, you can start the session. So we can give the basic introduction of PWSIM software and the DC-DC converters, and we'll see you
Sure. Okay, fine. Okay, yeah. Hi, good morning, everyone. So my name is Vinay. I am Power Electron Support Engineer in PWSIM. So today these are the topics from 9:30 to 11:15 we are going to discuss. So the first one is the introduction to the PWSIM software. So the next one is modeling of the DC to DC converter, which can here I'm showing the buck converter design. And the next one is the modeling of the three-phase VSI with the induction motor drive system with the field-oriented control. So, and the next one is the maximum power point tracking using the perturb and observe method. And the next one is the PWM generator with the 8 analog to digital converter in continuous mode for the TI target F28335. Okay, MCU. And then finally we'll discuss about the smart control software. Okay. So the first part is the PWSIM software. So just want to introduce some about the PWSIM software. So the PWSIM is developed by the PWSIM, and in 1994 in US, where the PWSIM is the exclusive distributor for the Europe, in Europe and as well as in India. But in India we have PWSIM. PWSIM is our company name, and PWSIM is our parent company. So here, PWSIM is used overall 70 countries and worldwide thousands of customers. Here you can see some of the customers like Samsung, John Deere, LG, Caterpillar, NASA. So these are. Okay, PWSIM is actually a very fast software and also the affordable, because based upon our requirement, we can choose the module where we can depends upon our application, project application. We can choose the our modules. So these are the some of the modules are available in the PSIM. So I will explain here clearly. So the first one is the basic module. So this is the mandatory module for any version, means any type of license. So this in this basic module, so every basic elements like a resistor, capacitor, inductor, and switches. So these are elements will be there, and even that voltmeter sources. So related functionality elements, everything will be there in that basic module. And later on, the add-on modules where the digital control module, the which is for the get domain analysis and for the microcontrollers, and also the digital PI controller, digital integrator. So these are all equipment elements will be there in the digital control module. And the next one is the motor drive module, where the motor drive module is for controls of the motors and drive systems. It is like just induction motor, or example, PWSIM motor, synchronous motor. So these are motor also present in this motor drive modules. Okay, the next one is the thermal module. So where we can find the heat loss of the switches, where MOSFET or diode or as IGBT, so where you can junction temperatures and switching losses you can we can get through this module directly, and you can create your own thermal module also, that is also available in this thermal module. And the next one is renewable energy module. So this is for a simulation of the wind and the solar systems, where you can get solar panel and wind turbine. So these are the and battery also. So these are renewable energy modules. So next one is SIM coupler module. This module is for interfacing with the PSIM with MATLAB. Means you can do the co-simulation with the PSIM and MATLAB. If it's example like if you have any control algorithm in the MATLAB, that you can work with the power circuit in the PSIM. Means you can run at that time and you will get output in the PSIM. And the next one, SIM coder. This is for actually for TA targets, and also auto code generation is available for the SIM coder module. Means these are the targets are available, F8 33, F8 803, and 806, 802, and 837. So these are the targets are available. So you can interface with these TA targets, and if when you don't need to write code again. So when you do the simulation, after that you can direct get auto code generation. Okay. And the next one is the design suits. So these design suits are for a motor control design suit and a hybrid electric vehicle design suits. So means when you give the inputs directly, so the output is like a fully schematic circuit with the stable control loops. Means you will get the stable output with the schematic with the different control algorithms like a dynamic torque control, maximum torque per ampere control, flux weakening control. This is actually available for the PWSIM motor and induction motor. Okay. And in the PWSIM motor, IPM motor and SPM motor both are available, but for the IPM motor, maximum torque per ampere control and flux weakening control, dynamic torque control is there. But for SPM motor, only flux weakening control is available. Okay, the next one is the smart control. This is the add-on software for the PSIM. It's another software. So this is for the controller designs, and also you can do the basic converter designs, and also you can design the converter like peak current control loops, average current control loops for the DC to DC converter that you can do, and also you can from the frequency response you will get you can generate the plant, and then you can directly implement the directly you can make the controller for the your own plant also, that is possible. And the next one is the mod coupler module. So this is for interfacing the PSIM with FPGA, means a model SIM software. Okay, where if you have any control algorithm code in the FPGA, so that if you want to see how it is working on the motor, that you can directly work with this module. So it will you can do the co-simulation with that code in Markup software and the power circuit in the PSIM. So you will get a output, and then you can analyze whether code is working or any errors in the output form that you can see. Okay. The next one is the Mac coupler and Mac coupler app. This is for interfacing PSIM with the JMAC software. So JMAC software is the electromechanical design, sorry, electromagnetic design software, means like a induction motor or PWSIM motor, like a reluctance motor. So these uh, electrical motors can be designed in the software. So if you want to see how that design is working, so that you can use this Mac coupler or Mac coupler RT module, and then you can do the co-simulation. Okay. Yeah. So you will get the output in the PSIM software. So the next one is the SPICE module. So where you can do the SPICE level analysis, and also you can create your SPICE circuits by using the netlist file. So that SPICE module is you can do the SPICE level analysis. And the next one is the PIF. So with this, you can check the software output. Sorry, uh, your code algorithm output. So okay, these are the modules are available in the PSIM software. So we'll go to the our DC to DC converter part. So here the classification of the DC to DC converters, where you can see classification is based on the construction wise and output and the power flow. Where the construction wise, there are like isolated and DC to DC converters and non-isolated DC to converters. You can with the
Yes, Vinay, 1 second. So
yeah
while you're talking, we are getting some noise from your end. So could you please check that? Some
noise.
speaker
Okay,
sound.
good sound. Wait 1 minute. Now is it fine?
No, still the sound is background sound is coming.
Sir, I think that mobile is near to the laptop that gives the sound.
Okay, okay,
That
fine,
echo,
fine.
correct.
Yeah, is it fine now?
Yes, perfect.
Yes, sir.
And one more thing, Vinay, just escape once the presentation and again open that, because we are seeing one more window blank. So
Is it?
yes. So now it's fine.
Okay,
Yes, fine.
okay,
So
okay.
still you can able to keep your mobile a little far away, please.
Okay, fine. Yeah.
Thanks. I can stop.
Okay. Yeah. Sorry for the disturbance. Yeah.
But
So,
still the
Vishwanath,
problem not solved, but okay. But okay.
okay, then I will switch off my mobile. That is better, I think. Yeah.
Okay. So if you're using mobile data, just check that. So those who are working with 32-bit, I'm going to share you the 32-bit installation link, but it is the old version. Right now we are using 12.0.3, but I'm sending the old version of 9.0.3. So for time being, so just work on that so you can install the same.
So now it is fine, Vishwanath?
Now, Vinay, I think
No.
some your earphones has the issue. I think so. Headsets.
Earphones, I will. So even though now it is, are you getting?
lightly. Okay, just continue. I think sound was little okay, so you can continue.
Okay, fine.
Yeah, Vinay, continue, please, Vinay.
Yeah, sure. So the classification is based on the construction. So where the construction is like isolated and non-isolated. Uh, where you can see here the isolated means where we can separate the ground. So based by using the some kind of transformer. So that is like a forward converters and flyback converters. And where the non-isolated converters are simple like using the switches and inductor and filter circuit. So where the buck converter and boost converters normal, these are the examples. And the based upon output also discontinuous and continuous. So these are the classification. So where continuous is the output of output current, whether it is continuous or discontinuous. So that is what another classification. And next one is the power flow, based on the power flow, whether it is unidirection or as bidirection. So where the bidirection, we know that where the in the battery charging applications or electric vehicle applications, we need to use the bidirection converters, whether for transferring the power in both directions. Yeah. So these are the characteristics, some of the characteristics I have listed here for the DC to DC converter circuits, where for the non-isolated and isolated converters. So the first one is the basic converters. It means that the basic converters are like a buck converter, boost converter, or buck boost. So these are the basic converters. So the number of parts means like the number of elements which are available, making that converter is very less comparing with the other converters which are present here. Okay, so the next one is the cost point of view. Because of the less components, the cost also obviously is less. And the next one is output panel. So where the output we can design for the output for the high or less, that is also matter here. And also ripple content is medium for the basic converters. Where it comes to the circuit converters, there will be some more elements like another inductor will be there. So these are another capacitor will be there. So these are the extra, some of the elements will be more. So first, that's why I have mentioned here as a medium. And also the ripple content in the circuit converter is very less. And the next one is the charge pump. Okay, this charge pump actually, this is with the switches and capacitor for the low voltage applications, where like very low power applications also we use this converter charge pump. And the next one is isolator. Where it comes to the forward transformer isolated converter, so the number of parts will be very large. So that's why the cost is very high, and we can use for the output power, high output power, and the ripple is the medium. And the flyback is the number of parts is the medium, and the cost is medium, and the power of medium, and ripple is high. Yeah. So these are the relationship between the switching frequency and the properties. Whereas if we consider the switching frequency, means we can use these power converters for MOSFETs or IGBTs in the different range of switching frequency. If you compare with the high switching frequency to low switching frequency, so yeah, the maximum efficiency is for the for low switching frequency, it is high, and for the high switching frequency, it is low, because when you give the high switching frequency, the switching losses also will be high. So that's why for the high switching frequency, the efficiency will be less, and the output current at the maximum efficiency. For the low switching frequency, maximum efficiency will get at light load. For high switching frequency, you will get the maximum efficiency at heavy loads. Where it comes to this ripple for low switching frequency, it will be large, because the charging and discharging time will be more in the inductor, because the switch frequency is low when then the timing of switch operation will be more. So that is the reason. So yeah, okay. That is the reason. So when it comes to the high switching frequency, the ripple content will be small. Okay. Because the time of operation switch is very less, so inductor doesn't need to store that much energy. So it can be very charge very fast, and it will discharge very fast. And the response speed for the low switching frequency, it is slow. For a high switching frequency, it will be fast. Yeah. So the next one is the isolated, non-isolated converters. These are some of the standard topologies. These are the standard topologies for the non-isolated converters. So here you can see the buck converter and the boost converter and buck boost converter, cut converter, and the SEPIC converters. So yeah, these are some standard topologies for the non-isolated converters. And these are the some of example for the isolated converter, where we can see here the transformers. So this is why that the separating the grounding. So this is what, as I said, number of elements which are used in the forward converter will be more. If you can compare with this here itself. Yeah. So the next one is the design of the buck converter. Yeah. Where the necessary, so these are the design steps where we can go for the necessary parameters of the power stage. First one means it will define the output voltage, input voltage, current. So these are the power stages. And next one is the filters design. When it comes to the filter here, the filter is the LC circuit. So we need to design the inductor, and also we need to design the capacitor. It means the selection. Okay. And the next one is the calculate the maximum switching current. This actually is for selecting the switch, because the maximum the switch current depends upon the maximum current which is flowing in the circuit. So that is also matter. The next one is the rectifier diode selection, where if you this is also another important factor, diode, because it needs to recover very fast. So that I will show in the future forward step. So the first one is the necessary parameters for the power stage. Where it comes to the power stage, the parameter input voltage range is also one other important factor, like what is the input voltage, and also in minimum voltage and the maximum voltage. And the next one is the what is the nominal output voltage. Okay. And the next one is the maximum output current. And so, and the maximum output current we need to define by, it depends upon the load. So that's what. And the next one is the switching frequency. Switching frequency is the one of the important factor which defines your converter size. Means the inductor size or capacitor size. So overall, it will and also it will be main part for the main impact on the efficiency part also. And the next one is the filter design. This is actually another important factor. You need to design the filter like LNC components with the maximum unity. Depends upon your output. Means what type of output you require. Based upon that, also you can design the filter. Okay. So next, first, so we'll go to the inductor selection. So where it comes to the inductor selection, here the important factor is delta IL, means the change in the inductor current, where you can take normally from 10 to 30% also. It depends on the output, which type of output you require, and also it depends if you take higher in the delta IL value, the inductor value will be less. So here you can see where if you increase the delta IL, the inductor size will be reduced. So that's what. And also, where if you increase the switching frequency, the inductor size will be reduced. And these are the actually this L value is calculated by using some loop equations in the standard topology of the buck converter, where you can see here in the left right side. So you will get this equation. So here you can see the higher the inductor value, the higher is the maximum output current based on the reduced ripple current. Means you, yeah. So how it is impact on the output current? That's what here I'm saying. So the next one is the maximum switching current. So here you can see the maximum duty cycle. There you can see the duty cycle is the V out by V in. That everyone knows actually. But also, even if it is come to the normal applications like hardware application, you need to consider the efficiency also. But in the simulation, it doesn't require to consider the efficiency. Okay, because maximum will use the ideal elements. But if you use the means your datasheet parameters in the type, so that then you go for the efficiency. Okay, and the next one is maximum input voltage is used because to lead the maximum switching current. So that means that I have already shown that their inputs it can be like a V input minimum and V input maximum. So here we are taking maximum input voltage because to find the maximum switching current, because when some cases we will get the input voltage will be maximum. So we have to consider the highest value. So because if in any case if we get the maximum value, so our converter will not get any effect. That's why we are considering the maximum values. And the next one is the next step in the calculating the maximum switch current is also determine the inductor ripple current. So how it is depends is here you can see depends upon the delta IL. So here you can see so this factor will check show the impact on the inductor design. That's what I'm mentioned here. Yeah. So this is what the maximum switch current is here. I not maximum is maximum output current because here you can see why we take to I naught is here. Here you can see I naught is this the load current value, and IC is the AC component which are present in the IR. Okay. So the AC component. So here the IL means inductor current is IC plus I naught. So where we are taking delta IL by 2 because upper part of the IC plus I naught we are considering. So that is why we are choosing here delta IL by 2 plus I naught maximum. Okay. So if we have inductor value, so but we need the ripple current. So in that case, we can use this formula. But here we doesn't require this formula because we already consider that our ripple, maybe it is like we can consider 10% or 20%. That depends upon our requirement, output requirement. Yeah. So next one is the rectifiers diode selection. Yeah. To reduce the losses, we can use the Schottky diode because it is having the fast recovery rate. So that is one option to use the diode, or we can use the MOSFET also because there will be another diode in the internal circuit of the MOSFET. So you can connect even the MOSFET also. Okay, and here the Schottky diodes have a much higher peak current rating than the average rating. Okay, so that's why if it is a higher peak current in the system also, that's why it's one of the reason that we are going for the Schottky diodes. Okay, and the next one is forward current. So average forward current. So this is the formula means the maximum output current into the 1 minus duty ratio. So this is maximum forward current formula. And the next one is power dissipation of the diode, where forward current plus forward voltage, sorry, multiplication to the forward voltage and forward current. So that's we will get the power dissipation in the diode. Okay, the next part will be output capacitor selection, where it comes to this is a minimum capacitance is needed. Means this is the formula for the minimum capacitance. So you beyond based on this, you can increase your capacitance value also. But for maintaining that output, required output, you need this minimum capacitance. So where here you can see the delta IL and the delta V naught. So delta IL we already defined what is the delta IL. So when it comes to the delta V naught, so we already have chosen our V naught value. So we need to know that means how much change if it is in the output is not a problem to us or else required to change. So that based on that we can choose the delta V naught. Okay. So based upon the delta V naught also the capacitor output value will increase or decrease. So here you can see when it is delta V naught is increasing, the capacitor value will be reduced. And also the same like this switching frequency, if it is increased, same it will show the effect that reduced output value of the capacitor. And in filter, there is another problem called ESR, means effective series resistance of the capacitor or else inductor. So because of this ESR, there will be some more ripple. So yeah, here you can see delta V of ESR. So ESR value into delta IL. So this is what this is how we are selecting the delta means the delta V output voltage. Okay. So the best practice is use lower ESR capacitor to minimize the ripple and on the output voltage. So this is what for reducing the ESR for minimum reducing the ripple content in the output voltage, better go for the low ESR capacitor values. Yeah, but yeah, and the ceramic capacitors are the good choice for the dielectric material X5R, and or better it is ESR is the effective series resistance actually. It is the internal resistance, series resistance of the capacitor or inductor. It can be. That depends upon even for the inductor, it will be there the ESR, and even for the capacitor. Okay. So yeah. So this is till here we have completed the the basic buck converter design has completed. Yes, yes. Equivalent series, sorry. Yes, yes, correct. So we'll go to the next one, modeling of the three-phase three-phase VSA fed induction motor drive system with the field-oriented control. So before going to that, we will just want to see some introduction of the induction motor and introduction of the field-oriented control. And next one is the VSA fed induction motor. So when it comes to the control strategy, there are two controls. One is the scalar type control, and another is the vector type. Where it comes to the scalar control, is like a Q-base control and all. But we can't use that more than the base speeds and all, because we can't increase the voltage more than the rated one. So there will be some problems if you can increase. So that's why we are going for the vector control. Okay. So we'll go to the first one, introduction of the induction motor. Any problem? Yeah. Okay. So, the introduction of the induction motor, we'll see here. So So the motor control industry is a very strong and aggressive sector to remind the new products and address in the several design constraints, including the cost
Sir,
reduction,
mute all.
reduction and the power factor correction and EMI radiation. So these are the problems we are in the motor industry, motor control industry, which are like a cost reduction and the power consumption reduction and power factor correction and reduced EMI radiation. So these are the main problems which are facing in the motor control industry. So for reducing these problems, so we need to go for the advanced control algorithms. So the embedded control technology is allowing the both high performance at the same time. The system cost reduction also can be achieved. So yeah, because we are now the majority of the induction industrial motor applications are AC induction motors. You can see if any industry, the maximum count of motor will be induction motor because it is very high. It is having some good features like higher robustness or higher reliability and lower price and a good efficiency means comparable. So these are the some good advantages having uh, induction motor. That's why every industry is going for the induction motor. But the use of induction motor also very difficult, means challenging task because for controlling there is a very complex mathematical model induction motor and also their non-linear behavior during the saturation and also the electrical parameter oscillations. So which depends on the physical influence of the temperature also. So these are some because of these problems for going induction motor is one of the big problem, and so far that we need for this these are the challenging tasks to reduce in the induction motor. So going to the fact that induction mechanism needs a relative difference between the motor speed and the flux speed. So this relative difference is called the slip. Here you can see that because when the induction motor, the stator will rotate it in the synchronous speed, but rotor will follow that synchronous speed, but it will be less than the synchronous speed. So that's what the yeah. And the next one is the slip must be present even when operating the field-oriented control region also. Okay, the rotor in the induction motor is not excited. I think yeah, induction motor is only single excited motor. It is not a double excited motor. If you take any DC motor or else other than DC series motor, any other motors maximum are the double and also PMSM. So if you go to any synchronous motor and all, those are the doubly excited motor. Means the rotor, we are exciting even the rotor, the same time stator also. For exciting the rotatory part rotor, there will be slip rings and pressures. So because of that slip ring and pressures, that it won't be much robust in the nature, and also it is expensive also, and also it requires continuous maintenance. But in the induction motor, it doesn't require any excitation for the rotor. So this is one added advantage for the induction motor because it doesn't need any expensive for slip rings and brushes, and there is no need of the maintenance, much maintenance. So these are the advantages, and also the torque production in the induction motor is like the angle between the rotor and the stator magnetic flux. So basically, the induction motor will work on the principle of the induction. So where when the flux is generated in the three phase, so that the same that the flux will be generating in the rotor part. So then linking of these two flux, the magnetic motive force means the torque will generate on the rotor part. So here you can see the induction motor rotor. So here you can see the speed cage bars means which are started in the end rings with the end rings. So because of this, we can say the induction motor is robust in the nature. And also this is the cut view of the induction motor, AC square phase induction motor, where you can see here the symbol omega. Ohm is the speed. Okay, so where you can see the stator flux, it will rotate in the speed of the synchronous, and where you can see the rotor rotation also in the direction of the synchronous. And the rotor flux will rotate in the speed of slip into the synchronous speed. So that's for the representation here. So yeah. The next one is the field oriented control. Okay, where it comes to the field oriented control, as I all said earlier, so the simple controls such as the P/F control strategy having some limitations on the performance. Okay, we can't increase the voltage beyond the rated value, and we can't increase the voltage frequency also rated value. So because of that, so many problems are like that's that's why we are going for the for achieving the better performance. We need a more complex control scheme is needed to be applied to control the induction motor. So the advanced control strategies can be implemented by using the mathematical transformation in order to decouple the torque generation and the magnetization functions in an AC induction motor. So yeah, here the first thing when we can when but we have the three-phase quantity in the AC induction motor, but we need to control the speed and the torque. So that three-phase quantity we are shifting to two-phase quantity and controlling the individually, like whether it is the Q-axis and D-axis quantities, and that we are controlling. So we can control the torque generation and also the flux generation, means speed also individually. Such a decoupled torque and magnetization control is commonly called the rotor flux control, or simply we can say FOC, field control, also field oriented control. Okay. So here you can see some picture representation is controlling the Q-axis current and I-axis current. Okay. In order to understand the field-oriented control technique, we'll start with the DC separately excited DC motor. Here you can see separately excited DC motor. You can control individually, where we can control the armature by using separately and also field separately. Okay. So yeah, the electrical study of the DC motor shows that the produced torque and flux can be independently tuned. Okay, so that's why we this is the technique which are implementing in the FOC. Okay. The windings are managed to keep the flux produced by the rotor winding orthogonal to the stator field. So this is because when it is orthogonal to the stator field, only it can be produced the maximum torque also. But in induction motor, only one source that can be controlled. Okay, because we that is a stator current only. We can't control the rotor side part. So that is one more difficult part in the FOC. So here, I think you understood that the goal of this is FOC imitating with the DC motor operation. So this is the block representation of the field-oriented control, where you can see the three-phase inverter and the AC motor. So here you can see here three-phase quantity here ABC. Actually, I should represent. Okay. So here the three-phase quantity I'm converting it to the two-phase quantity, but still it is in the rotatory frame only. Okay, three-phase it is three-phase quantities are in the rotatory frame, and also the alpha beta which are generating also rotatory frame, but it is in the two-phase quantity. So we need to make it in the stationary frame because to control the is really easy. So that's why we are from the part transformation we are using alpha beta to DQ transformation. Okay, so where we'll get IQ and ID. So you can here you can see the when we give that depends upon our requirement, we can change the reference value. So when we give the reference value, so it will generate the negative feedback. So that the error signal is tuning by PI controller. So the PI controller will generate the V-axis voltage and Q-axis voltage. So by using the inverse Burke transformation from DQ frame to uh, alpha beta, means rotatory frame we are converting again, that we are using for this state vector, space vector PWM. So another thing here we see state vector PWM also very important, because it is having much advantages comparing with the sine PWM, and all. Means we can utilize the source I think nearly 15% more than the sine PWM. Yeah. So some advantages and also ripple content will be less comparing with the sine PWM. So these are the advantages. So that's why we are going for the state vector PWM. Okay. So actually, okay. First of all, we have seen that three-phase quantities should convert into the two-phase quantity. Okay, that is fine. But how we can convert, that is another task here. So that here you can see the three-phase voltages, currents, fluxes of the AC motors can be analyzed in the terms of the complex phase vector. So this is the complex current vector which is generating by using this formula. Okay. So by assuming the IA and IB and IC, means the three-phase currents are the instantaneous currents in the stator phase, then the complex stator current vector is defined here. So this is where that we are generating the complex current vector by using the IB and IC. So the next one is transformation, means from ABC to alpha beta projection. It is like from ABC is a state rotatory frame elements, and when it comes to the alpha beta also rotatory frame elements. So, but it is alpha beta in two phase. Means here you can say the space vector can be reported in another reference frame orthogonal axis called the alpha beta. Yeah. The projection that modifies the three-phase system into the alpha beta means, which means that which means the two-dimension orthogonal system in present below here you can see. So yeah. So the two-phase alpha beta currents are still depends upon the time and the speed. So that's why I'm telling that the alpha beta also still it is in the rotatory frame. So we need to convert that in the stationary frame, which we can convert in the by using Burke transformation. So here you can see from alpha beta to DQ projection. So this is called Burke transformation, where you can see this projection modifies the two-phase orthogonal system into DQ reference frame. Consider the d-axis aligned with the rotor flux, and consider the q-axis shows the relation from the two reference frame from the current vector. Okay. So when it comes to the d-axis current, which we can control the flux component, okay, and q-axis current, which we can, by using the q-axis current, we can control the torque component. Okay. So yeah. So by generating like this, so here also we are generating by using the DQ reference frame. We are generating the same complex current. So that's why the final element will not the output will not change, but the way of we are controlling is changing here. So yeah. So these are the main important factors which we for operating the field-oriented control. Okay. So yeah. So these are the some few advantages. Means improve the it will improve the torque response, and also torque control at the low frequency and the low speeds is possible, because we are controlling individually. There it doesn't need So that's why we can control at any point. And next one is the dynamic speed accuracy. So yeah, because we can control the flux by using that ID. So where the flux is inversely proportional to the speed also. So when you increase the current, so flux will be reduced, inverse vice versa. And the reduction in the size of motor and cost and the power consumption also, because it is one of the most efficient method. So that's why. And the next one is uh, four quadrant operation is possible with the field oriented control. And next one is the short term overload capability also available for this. Okay, so the field oriented control is over. The next part is maximum power point tracking by using the step and observe method. Okay, so where you can see here, wait, I think it better to show you people first this how we are implemented this field oriented control in the simulation. So we go to the software and I will explain. Then I will go to the solar. So here you can see. So this is the G of the PSIM software, where you can see elements. So here this is the library of the PSIM software. So here you can see every elements are there. And when you this is the creating for new file. When you create a new file, so this all will be activated. So these are the used elements. So most useful elements for every operation for the power electronics. So yeah, the next one is here. If you see the elements, the first one here you can see the power library where the RLC branches, the switches, and transformers. Here you can see the different types of switches are available, and where the resistance means branches are available. And the next one is the switches where you can find the different types of switches. If you can see here, the SP means it means that it supports the SPICE. So where you can use this elements for the SPICE analysis also, and the magnetic elements, and so till here the basic means you will, these are the required. These are in the basic module. When it comes to the motor drive module, where you will get different types of motors are available here. So here you can see the squirrel cage induction motor and wound rotor induction machine PMSM. So these are the SRM. So these are the motors are available, motor drive module. So when it comes to the Mac coupler and Mac coupler rectifier with the JMac software interface modules are there. And these are the different types of sensors are available in the PC. And the next one is the thermal. So these are the thermal MOSFET IGBT. So these are available. The next one is the renewable energy. So here you can see the solar module and also wind turbine lithium battery. So basically, we in the PCM we have the lithium batteries, and also you can design your own battery. Means you can give the data specifications. Okay. Next one is the control, where you can get the filters, compensate computation blocks. So all type of control blocks are available in this. So next one is the other, means where you can get the AC sweep analysis, parameter sweep analysis. So probe sensors, so that you will get. And next one is SPICE. So these are the SPICE directive block. And yeah. So next one is the symbols and event control and sim coder, the target code generation and all, and for TI targets. So these are the library. So here you can see when you click on this, so you can directly click on this, and you can click anywhere wherever you want. And yeah, if you do right click, so here that it will be rotation also, that is possible. Yes. So okay. So we go to the, I will show the, so here in the help we can search if you, oh, sorry. So in these examples, so motor drive module, where you can find the, so these are the examples are available, and yeah. So here you can see induction motor, field oriented control. So yeah. So this is the one of the examples we have. So here you can see this is a induction motor, field oriented control. So where you can see here, this is the inverter part, and where you can see here, these are the ammeters. So to monitor the current, and where you can see these are the sensors, current sensors to get the current signal. And also these are the low pass filters, and this is the ABCD to DQ transformation diag. Here it doesn't require alpha beta because it is directly converting ABCD to EQ current. So where we get the IQ and the ID currents. So that we are using here ID and IQ. So yeah. So here you can see 1 minute. Yeah. So here you can see this is a speed sensor where you will get the speed output in RPM, and this is the torque constant load. So constant torque mechanical load. So yeah, here you can see this is the ID current. So this is the ID current where you are able to control the speed of the machine. So this is the input given, and here it is the speed speed reference we are getting. So and also here from here the speed whatever we took that we are giving here. So it will generate the slip from using the constant with some calculation. So we are able to generate the slip. So where we are by the slip we are getting by integrating we are getting the theta value. Okay, and the next one part here is the speed. We are whatever the speed we are getting that we are giving the error tuning signal. And we are generating the IQ. So here you can see by using the IQ. So we are getting the PI controller VQ and I. So by using the PI controller, we are tuning the error signal which is on the IQ, so that we are getting the VQ. Okay. So this is the limiter for giving red output. So from VD and VQ, we are getting three-phase quantity by using the DQ to three-phase AC converter, sorry, block. So where we are giving the sign. Okay. So where we are giving the to the switching frequency is the 10 kilohertz. So where we are getting the pulses. So the pulses we are giving to the this activities. So we can run this block and we can see the outputs. Yeah. So once it is a complete simulation, so we'll display the SimView window. So this SimView window, we select whichever the output we require, and so you will get the output. So this is the three-phase current we are getting from the inverter. Okay. Yeah. So this is the field-oriented control system for the induction motor.
Sir, from
Yes,
where
yes.
we are getting this model? Sir, from where we are getting this model?
Actually, this will not work in the demo version, so that's why I'm telling. Actually,
Okay, sir.
because actually
Okay.
in demo version there is a limitation for 30 elements, right? 32 elements. That's why we can't implement this in the demo version. Okay.
Okay.
But you can able to see, so Islam, so you can go to help option over there after window and type FOC. So you get the FOC of induction motor. So this entire algorithm you can able to in the demo version, but you can't able to run.
Here you can see FOC. So when you type the FOC,
so we have a video tutorials and documents also. For the documents, you can able to refer all this part. So the second one, so main PWSIM FOC drive. So just click on the help browser.
Okay. Okay, sir.
You are
Thank
able
you.
to see, but you can't able to run. That is the only thing. Okay.
Okay, sir. Okay. Thank you.
So, yeah. Okay, fine. This is the field oriented control implementation in the induction motor. So we'll go to the next topic. Yeah. So the next topic is the maximum power point track by using the pattern and observe method. So we can see what is the maximum power point track first of all. Because from the solar panel we can get the maximum power because the load resistance, load internal resistance and source internal resistance will be differ. So when the load internal resistance and the source internal resistance are same matches, then only the maximum power can be transferred. This is the maximum power transfer theorem also. So that is what we need to implement here. And also that we can implement by different algorithms like better and observe method, incremental conductance method. Some more algorithms also is there. But here I am just showing how it is implementing by using the better and observe method. So, and this is the basic structure for Pvt implementing, where you can see the solar panel input. So the solar panel, you can see that our inputs are like irradiance. Okay, so the irradiance for in the standard test case, the irradiance are 1,000, but it won't be like when you are testing in the outside this physical module. So it never feel like 1,000 because it will continuously vary the irradiance. The next one is the temperature. The standard test is temperature is 25 degrees, but in the output means in the physically, if you check, it will continuously vary. Okay, that's why actually another challenging the MPPT algorithm is continuously it will check the outputs of the solar panel, and according to that, it will generate the duty ratio for the DC to DC converter. So that's why we are able to control the power output, the maximum power output we can get, but it is very difficult to control the output voltage from the converter. There you can see here. So this is the MPPT algorithm normally for the perturb and observe method, where you can see first one is the sample samples which we are getting from the solar panel. Here in this block you can see. So this is a from this we will get current and voltage samples. Okay, so by using the current and voltage samples, we are calculating the power. Okay, so power and that power actually here in this block, this is the decision block, which means in this block we can see the previous power. If the present power is whether greater than or less than of the previous power. Okay, so if it is greater than the previous power, then we'll go to the S means block. Okay. So in this block, it is like before it is actually compared with the power, but now it is going to compare with the voltage, where you can see the voltage, whether the previous voltage is more than the present voltage or not. If it is present voltage more than the previous voltage, then it will go for the increment. If not, it will decrease the PWM because previous voltage is greater than and then the present voltage means. So it will try to get the previous voltage. So that's why it will decrease. Okay. So same like here. See when it is the previous when it compares to the previous power is more, then it is when previous voltage is less than the greater than the sorry present voltage is greater than the previous voltage, then it will go for the decrease the PW, or else it will go to the increase the PW. finally you will get the what is the so this is what you will get is the same algorithm will continuously it will repeat. Okay, so yeah, we'll go to the software and check once this. Yeah, then yeah, sorry. And here in those examples, we can open example. Yeah, we will share, sir. We will share the PPT after this session. So where you can go to the renewable energy, solar power, and here you can see better and observe method. So you can run. So here you can see this is the input, the solar panel, and these are the irradiance input we are giving. Okay. So where we can select the so where you can select see the what is the maximum power and what is the output power we got. See here in the red line we can see that this is the maximum power. Okay, and the pattern and observe that try to always follow the maximum power. So here you can see it is trying to because it is continuously increasing PWM. So that's why this is always like a variation will be there, and but you will get the output power as expected. Okay, and yeah. So here you can see this is the buck converter, and where you can see because this capacitor is for yeah, this capacitor is for the because the output voltage of the solar panel always like oscillating, right? So that's why we need capacitor here. Then yeah, so okay, so and we can go further more. Yeah, here you can see the battery voltages. So yeah, so the battery voltage is maintaining that constantly from this and cell. So this is the cell voltage. So this is the outputs, and in this you can even see the maximum value, minimum value, and even you can analysis the FFT and the average control power, RMS value, and the power factor control and real power, apparent power. So these are the so many options are there for the analysis. Okay. So here in this block, it will implement the full. It will implement the observe method algorithm. Okay, so this will we can see. Yeah. So we'll go to the our PPT. So yeah, so finally we have done the maximum power point tracking by using the and observe method. Okay, so here I have used the load as the battery, then I have shown the output also, how it is coming and how implemented in the software. So we go to the next one. So this is actually PW. So this is for the PWM generation. Okay, with analog to digital converter in continuous mode of the PI target, which is 28335 MCU. So from the TI targets, we can directly get, we can generate the PWM signal. And here you can see this is the ADC, which is converting analog domain to digital domain. And this is the DSP voltmeter, means you can see, you can forward this voltage, whatever you're getting, that we can use for the DSP operations. Okay, by using this DSP clock. And in this board configuration, so we every in this board configuration, so we have to configure the pins which are required for the PWM generation. So that we need to do, and here the interrupt generation. But actually, this interrupt will not trigger anything in the ADC because it is continuous generation, continuous mode. Okay. So, and this is the output from the packet double 35. So where you can see the PWM A. So this is the output, and also PWM B, where is a complement of the PWM A. So I will show this in software. So we can go to the examples and open examples and SIM coder, and in this 335 target, and in this PWM generation, and in this continuous mode operation. So this is what the target I have shown there. So once it will go to the board configuration. So yeah, so this is the board configuration. Entire pins, every pins will be available here. So depends upon our requirements. We can select the pins where you can see here PWM. This is GPI 00. So GPI 01. So these two pins I have activated here, and the next one is the serial port pins. Two serial port pins I have activated, and the next one is digital output also I have activated for the ADC. So yeah, so these are all the pins I have activated. Once if I activate, means if it is yeah. So once if I just want to activate this pin, after clicking that, we need to log this. Okay, and so once if I log, then we can close. So it will show there. And this is the DSP clock where you can see the external clock and DSP speed. And this is for SIC configuration for the DSP operation. Okay. So this is for ADC for SIC. So where you see the ADC. So this is the ADC, and you need to give you need to select the pins. So where you have selected the continuous mode, so that doesn't require anything. So single port we are using here. So because of that single port we are using, and remaining ports we have data short to the ground. And yeah, so here you can see this is the PWM block. So where you can select the sampling frequency and the dead time, and the switching frequency scaling factor, and the peak to peak value. So this is these are the inputs we need to assign. Once if we assign the inputs, then we can here you can see the start PWM at beginning, or you can see whether if you want to start PWM or not. That is also you can decide. And yeah, so where you see the digital output. So here you can see the digital output. So for seeing that output, you have configured that here the switch means this is for showing the name of this output. So where you can see the name. So after selecting that, see here it is displayed the name. So yeah, in the next one here on the source. So here we are giving the sawtooth waveform in the frequency of the 100 edges. So yeah, and the peak value is 1. Okay, and this actually this is output for the this target PWM, and this is normal conventional method of PWM. So we can, for comparison purpose, I have keep here. So first we'll go for the run option. Yeah, it will take very less time. Even you can see where you can see PWM A. So this is what the PWM A you will get, and even you can add here another screen, add to screen. Okay, so you can see in the PWM B. Okay, so see here you can see that the both PWM signals are the complementary each other. Okay, so here you can see the opposite the And the next block, next window, you can add a PWMA1. This is actually conventional PWM, which is generated by the sawtooth waveform. Sorry, yeah, with a triangular waveform. Here you can see this is a triangular signal with 10 kilohertz. So what the frequency we have given here, that see, that is sampling frequency, same sampling frequency we are giving here. Here you can see the sampling frequency. It depends upon the time, right? So that's what. And this is here you can see this is another important factor in the simulation, simulation control. So where you can give the step time and the total time. So depends upon the step time, the output means clarity, everything will be changed, and this total time will defines the how much time the simulation should run. Okay, that is these both are the two important factors. But actually, in the PWSIM is the fixed step time. So once you pick you, it will automatically will see whether it is convenient for the simulation or not. If not, it will change automatically. So this is for the when you are running the spice operation. So for that, this is the in that time you can give the inputs from the spice simulation, and this is for the target. So in the in this encoder, uh, you have to select here the hardware target, which target I'm using here. So in the F2833 in that version, I'm using F28335. So that's what I have mentioned here. So we need to mention, then only we can able to run the simulation. Okay. So yeah, after running, yeah. So this is actually voltage probe. This is voltage probe to see the sawtooth waveform, and these are the voltage probe to see the waveform, and this is the input to see the digital output. Okay, so where you can run, yeah. So yeah, here the PWMA and PWMB. So these are the PWM generated by the target, means FT8335. And this PWM is generated by using the conventional circuit, which is this one. Okay. So whatever this generates, same thing only it is generating here also. So that you can compare like this in your window. You can see the you can compare PWA1 and PWA. So both are will be same. Okay. So yeah. So the next one is you can see the digital output also, where you can see the digital output is ADC. So, yeah, so this is what so ADC, and the next one is you can add. This is the V input from the sawtooth waveform. This is the sawtooth waveform we are playing, and the next one is interrupt. Yeah. So these are all things you can see. Wait, let me show. So this is the output you are getting. So means whatever the value, this is what the input of the sawtooth. That's what I shown. Okay. And here after running, even you can then you can generate the code. Here you can see generate the code. So you can directly generate the code, means for the particular target with the header files, and with header files and the date to time, everything you can see here. So you can note this date, and after that, where is the target? Yeah, sorry. So once you come here, you can go and open the generate code folder. So whatever the code we generated, that we can open here. So in this, you can find the overall every files, like project files and C files and command files and H files. So these library files. So every files you can see and you can directly use in the code composition studio and debug the code in the database. So this is the one added good advantages in the PSIM. So yeah, the next one, we'll go for the next one. Yeah. So yeah, the next one is smart control software. So this is a software for the controller design and even for the DC to DC converter design, and even for the hardware in loop also you can do with this board will be there for this. So this is the so yeah, how to generate code. I have shown here already. So once I will show it. So this is the right. So once if you configure everything, whether when it is running successfully, so here you can see the simulation. This is the PSIM simulation. Okay, and you run the simulation, so everything is fine. First seeing the you can see the output, and the next one is here in the simulate option. You can go for the code, generate the code. Okay, so it directly generated the code. Here you can see, but yeah, it is directly generated the full code for directly for the TI targets. Okay, so this code we don't know where it is actually. So that's why we can go. It is generated, but we don't know where it generated. So we can go for the here in the option after below the generate the code option only. Open the generate code folder. Once if you go to the folder, so directly you will get everything from there. Means like project file, C file, command file, H file, library file. So this all you will get, and you can use this in the code compilation studio for TI targets. Okay. Your own plan. Yeah, you can actually by using the code compilation studio only, you can directly you can debug the code, and even you can use the PIL also. That is also option is available. Okay, the next one here, you can generate your own plant by using the you predefined topologies, or else by using the frequency response also. By importing the frequency response also, you can generate your plant, and you can generate your control algorithm, and you can select your control algorithm, whether it peak current control mode, open average current control mode, or else it's like voltage control mode, current control mode, something like that. Okay, and the next one is the solution map. So after generating this topology by using this so the next one is the solution map. So where you will get solution map to fine tune the your control loop. Means by using the cursor you can tune the output values for your required thing. So that is what the solution map, and this is the output details, and where you can get plots like a Bode plot, Nyquist plot, and all. So that after that you can directly you can take the outputs from this, or else you can you can export to the PSIM software also. So yeah, the smart control, actually this is the I have said you already, it is a controller design software specifically for the power electronics application. Okay, and it is very friendly interface that you can understand very easily, and is simpler to understand. Display, stability and performance also. And yeah, the Smart Control Pro, it adds the digital control design option, where you can do design in the digital control loops with using the digital equipment. So that's what the Smart Control Pro. So the control design from the specification. That's what I have already said that when you give the inputs, automatically it will generate the output by using best control for your converter. So this is what, even in analog domain and digital domain, both we can choose in our option. And it is actually possible for the multi-loop control structures, where you can see average current control mode and peak current control mode. So these both you can see, and even in the average current control mode, inner and outer loop compensator design also available, and the peak current control mode compensating the ramp design and the high frequency effects also you can choose in this. So the next one is all data is the real-time update. So, here you can see the when you are changing in the response plot, directly you can see the what happening in the output plots that you can from the body plot, Nyquist plot, you can see, and you can see the output how it is varying. That is by changes in the controller. So this is possible in the this smart control software. So this is what solution space. The white color, whatever is there. So this is the possible solution space for getting good design for the controller. So here you can see the solution map helps for the user to choose the crossover frequency and the phase margin. So that's what first choosing the crossover frequency and phase margin you can by in the cursor you can change for sure that in that. So the next one is that here you can directly you will get the steady state output waveforms where you can see current voltage and inductor voltage, so everything you will get. And electronic circuit simulator integration. Okay, so when you can see, so smart control is the seamlessly integrated with the PSIM and electronic simulator. So when you generate the circuit design in the smart control, directly you can import to the export to the PSIM, and you can do the simulation further analysis in the PSIM software. That's what I have mentioned here. And the smart control automatically generate a ready to simulate schematic. That's what means you can directly import export to the PSIM and complete power stage and the control stage. Okay, and with only one click PSIM icon, then one can export to the entire circuit simulation in it. So that's what. So you will directly here you can see PSIM symbol. So but after the design, you can directly click on that. You will get you can directly import this circuit into the PSIM software. And next one is that you can import even frequency response when you do the AC sweep analysis in the PSIM software, because sometimes maybe your whatever the plant you are using it will be different, so that will not be the predefined topology or something. So that time you can do the AC sweep analysis for your plant. With that frequency response, you can import the frequency response in the smart control, and you can define your plant, and after that you can define the your control algorithm, so that you will get stable output stable output, and also you can tune the parameters. It's like PI signals, and then you can tune values, and then you can tune. That's what. So yeah, we go to the software smart control. So I will explain you. Yeah. So here you can see the symbol called launch or export to the smart control. Okay. Once if we go to the directly click on the smart control, so you will get this space where you can close if you want. So here you can see where you can see the DC to DC power stage, control stage. So this is actually demo version. So even for this, having the limitations like DC to DC converter, peak current mode control, and DC to DC converter, average current mode control, and power factor correction boost converter. So these are the topologies are available already. Even here you can see S domain model editor. So here you can edit your own uh, plant, and here you can see the import frequency response data from text file. So whatever the frequency response you generated in the PSIM or any software, that you can directly import here frequency response, and you can create your own model for your own plant for this option. Okay, and even if you have any equation regarding your circuit, that by using that circuit also you can directly create your own plant, and you can do the operation. Okay, so here DC to power stage. So yeah, so here you can see once if you go to the here, yeah. So this is what so where you can, this is actually GA of the software. So where you can go for the design. So predefined topologies, and here you can see single loop, peak loop, means directly you can select. So this is what the buck converter design. Or here you can see there are some buck converter L means L current sensor. This is voltage mode control. This is current mode control. This is boost voltage mode control, current mode control, and boost diode current sensor sensed, and buck boost and buck boost voltage mode and current mode, and the flyback and forward. So these are the converters are available in the smart control. But for the demo version, only buck converter with voltage mode control for understanding only. See, if you click on any other control mode, so it won't show because it is demo version. So once you go to voltage, then it is fine. It is in voltage mode control. So here in the sensors, because it is a voltage mode control, we need to sense the output voltage. So there, here you can see there are three types of voltage sensors. One is voltage divider and embedded voltage divider, and isolated. So you can select here and if you want to, if you click on the voltage sensor, can you please mute someone?
ಎಷ್ಟೊಂದು ಸಾಫ್ಟ್ವೇರ್ಸ್ ಇದೆ ಮೇಡಮ್ ಎಲೆಕ್ಟ್ರಿಕಲ್ ರಿಲೇಟೆಡ್ ಚೆನ್ನಾಗಿದೆ ವರ್ಕ್ಶಾಪ್ EMTP ಪ್ರಾಜೆಕ್ಟ್.
Can you please mute? Yeah, fine. So here you can select the gain, and here you can select the reference voltage, and here you can see the output voltage. This output voltage actually we have defined in the input parameters. So this is we can't change. The reference voltage must be less than the output voltage. Okay. So that's what transition. Next one is here you can see here these are the controllers are available for the buck converter. For if you go for some other converter, there will be some other more controls also available. For here type 2, type 3, type PI controller. So we can go for, oh sorry, this will not work. So type 3 will work here. So when we go to the type 3, so here you can select the resistance, and even the switching frequency also we have defined in the plan. So this and here you can see rise time, and this all the parameters we need to fill. Yeah. So here you can see these are the input parameters. This switching frequency we have given 250 kHz, and here you can see the inductor resistance. So these are values. Okay, output under. So once if it is everything fine, then you can go for play. And so before that, before going for okay, you need to keep you need to give the crossover frequency and the phase margin. So for that, this is the solution map. So we can click somewhere. So we'll get the clock crossover frequency and phase margin, and we can go for the okay. So once if you go, so this is what the output loop you will output GA you will get. So where here you can see the body plot, Nyquist plot, everything is there. Here you can see the output reference step voltage output reference. So once if you go for this, uh, once once if you click on that solution map, and when you are changing the continuously, so here you can see the how output is affecting and how this V naught is changing the value, and how, so depends. We can tune the parameters and we can see okay. So when we feel that this is fine, so here you can see. So this is, so this is the output. It is fine for us. So we can see. Then we can exit this. So yeah. So here you can see this is the crossover frequency and phase margin. So the values, and here you can see this crossover frequency. So after everything, you, if you want to see what under the inputs you have given, what under outputs you got, so here you can see view input data. So where you will get the input data. So here you can see the frequency range and crossover frequency what you have selected in the starting. And the next one is the plant. This is the actual plant, means which is the converter. So the resistance, inductance, capacitors. So how much you have given, every values are displayed here. And this is the controller design. And yeah, so this is the sensor design inputs and the compensator inputs. And these are the inputs what you have given. And these are the outputs what you have getting from the, you know, from the this point, means from output. So where you can see the compensator results, where you can see the R value, C value, so frequencies value, crossover frequency values, and all. So here you can see the sensor values. So these are the output values. Okay, and so here you can export to the PSIM option. It is there. And next one, I will generate the report. Yeah. So here you can see, you can generate the report in the notepad. What are the inputs you have given and what are the output you have got. So here you can see. Okay. So here you, okay, sorry, for the demo it is not there. So once if you click on the PSIM export to the PSIM, directly this model, full model you will get PSIM schematic output that you can open in the PSIM software. Okay, and here you can see this is what I have said, you right, the output values and all. So these are the output values like inductor voltage, sorry, inductor current and the output voltage. So everything you will get here. Okay. So yeah. So the next so okay, I think what we have cleared is everything fine. I think first one. So this is what we have cleared. I have given the basic introduction of the PSIM software. And the next one is the modeling of the DC to DC converter, which means the buck converter we have seen. That converter we are going to implement in the hands-on in next means after 11:30 we are going to implement in the PSIM hands-on will do. And this model along of the three-phase VSFI induction motor drive with the field-oriented control. So this we have seen about the VS, what is the field-oriented control advantages, and we have shown you. And the next one, the PSIM schematic simulation also have shown you. So that's the next one. is the maximum power point tracking by using the pet up and observe method. Also, I have shown you. So I think everyone understood. Okay. And the next one is PW generation by using with the analog to digital converter in continuous mode of operation with TI target F28335. So this is also very clear. And the overview of the smart control. Okay, I think we have cleared this everything. So hope everyone can take 15 minutes break. So you can go for the refreshment and we'll get back to you by.
So meantime, you can install if someone is not install the software, and we'll start with the hands-on.
Thank you, sir.
11:30. Yeah, we can meet at 11:30. So if anybody not install the software, please start installing at least now, so we can
Yes,
we
and
don't.
it will take 2 minutes to install the software. We have already shared the links to all the participants. So if you didn't receive the links, let us know. We'll share it.
Okay.
Sir, excuse me, sir.
Yes.
Yes.
Sir, that demo version only, I mean, works only 32 elements only like that came, na, sir?
Correct.
Is that the
Correct.
same software is helpful us?
Yes, it will be helpful. So it's basically for understanding of the software we are setting to. We'll do a couple of exercises on the same software.
Yeah, these examples and all will cover means that we'll install the same thing, sir. Otherwise, the pirated version, anything if you want means that we'll install that.
Version. Sorry, sir, we don't have any pirated version. So we will install. We'll show you the software, which we'll show you the examples, which will help you in the demo version itself. So don't worry on that.
Okay, sir. Okay, thank you, sir.
Okay, fine.
So just have the 20 minutes, 15 minutes refreshment, and by 11:30 we'll start the session. Thank you.
Yeah,
So
sure.
I'm just muting everyone, so we can go for the break and come back.
Yeah.
Just you can take the break and come
Thank
back.
you, everyone. So you can take some time for the break, and we'll get back to you. Thank you. So, okay, welcome back everyone. I think everyone have came back, right? So, okay, we'll start the second session. So, which is a power electronics hands-on. Okay. So now we are going to implement the buck converter and the boost converter in PSIM software, which can implement in the demo version. Okay. So, and the next part is AC sweep for finding the uh, phase and frequency. And the next one is the parameter sweep for finding the best which is suitable element requires. Okay, thank you. So yeah, so the first one is the design of the buck and boost converters, and which you can implement in our demo version itself. And the next one is the AC sweep parameters and finding the phase and frequency. And the next one is the parameter sweep. So finding the means suitable element, means by changing the, it is like just doing the sweep analysis which value of the resistor which can be suitable for the operation that we can see, and we can see the how the resistance value is changing, that how it will affects the voltage, or else if it is L value, inductor value, if it changes, how it is affecting the output. That like that we can see in this parameter sweep. So the next one is the designing of the VSI inverter of induction modulation in PWSIM. So this is just normal VSI inverter to induction motor. Okay, I will show how to make it. And the next one is the introduction to the Power4 software. So the Power4 software is actually it is a one converter design software where you can design the converter and you can explore with the many types of topologies and many types of means you can do the frequency sweep analysis, and you can do the you can get the output. So it will be very helpful software. So I will show that also in the last step. And the next one, designing the three-phase DC to three-phase AC converter. In Power4 software, and I will show how that import in the PSIM software also. Okay. Yeah. So we'll start our session. So here you can see the designing of the converter in PSIM. So this is the way we need to design the circuit simulation. So where we can give the input voltage.
One sec. So
Yeah.
we have shared the feedback form in the chat window. So just fill it and submit it. Accordingly, you'll get the e-certificate from the college. So if anyone is not able to get the link, let us know. We'll share you again. We have shared again. So just go through it and please submit it. Yes, we can start. Yes.
Okay. So you can open your PSIM software. So on whatever we provide, the software you can open, and you can just follow the instruction. Whether if you get any doubt, you can chat in the chat box. You can message in the chat box. So after open, you just click to new document creation. So once if you create the new document, you will you can find this. So yeah.
Yes, this part you can start slowly. So you just show the overview of GUI of the software once, various elements and commonly used blocks, and so parallelly they can open the screen and they can work out, because they have to see the document link plus PSIM link, right? So slowly show one by one, and they can able to follow back.
Yeah. Okay. Fine. So these are this is the way. Mostly our required elements maximum for the power electronics you can find here, but here in the elements also we can get. So where you can go for the power elements and power elements and power. So all type of branches you will get here. So RS, RC. So these are the branches you will get. So and also switches you will get here. What are the type of switches you will require? Sorry, these are the transformers. These are the switches, MOSFET diode, and IGBT. So everything you will get here. So yeah, the next one is the transformers and transformers you will get here, and magnetic elements you can see, the op amps, coupler. So these all blocks you will get here. So motors, squirrel cage induction motor, wound rotor induction motor, DC motor, brushless DC motor, PMSM, and SR. So these are you will get here. And next one is the Mac coupler model. So this is the module for GMAC software, and then this is a mechanical load sensors. So we will use actually this, one of the sensor in this for the yeah, induction motor, VS effect induction motor. Yeah. Then next one is the thermal module. So where you can see here in this, you can get junction temperature, switching losses, everything you will get in this. I will show later everything. So this is the renewable energy model. So where you can get the battery also and the solar panel. So here you can see. So these are the parameters. You can fill the battery. So these are maximum data parameters. So you can fill and you can use for the simulation. Yeah. So coming to our buck converter. So here you can see what and all elements are required. First one is the source and switch and diode and inductor, capacitor and resistance. So these are the main power elements are required. So once if we go here, sources, the power. Once if you go to the sources, you can find the voltage source. So in this voltage source, we need DC voltage source. So here you can click. So you will get the DC voltage source. Okay. So for us, you can take from here itself. Down there is a project view, library browser. So there you will get everything. Or one thing you can do. Yeah. So if you go to the view and you can activate the library browser. Once you can activate the library browser, you can see the library browser here. You can find everything in somewhat easy way. So where you can see the sources. So voltage source. So this what you can directly click on that and you will get directly and you can place wherever you want. So the next one is the MOSFET, where you can find in the switches. So in these switches, so there are types of MOSFETs also available. So we will go for the normal MOSFET. So for keeping the MOSFET, we can, if you use the right key, mouse, if you use the right key on the mouse, so it will rotate. So we can keep which direction we require. So we can keep in this direction. So the next one, yeah, okay, thank you. So the next one is so here you can see which is the diode and the inductor is the required thing. So where you get a diode here, so you can use the right key. You can keep here. So you make sure that the anode and cathode directions are perfect. And then after you go for the RLC branches where you can find the inductor. So where you can keep here. And the next one is capacitor. So if you click on the right key, it will rotate. And the next one is the resistor. Resistor which can be the load. When if you for your purpose you may require a battery or something also that you can.
Hello, hello,
Yes,
sir.
yes, yes.
Sir,
Tell me.
when I'm picking up the sources, it is showing multiple times the same source. Means two, three times it
Because
is.
maybe you have clicked just delete everything and take new one. That is fine.
Okay,
Just click once, and after that, please press the exit button. Exit button. Okay. Then that will
okay,
leave. So
okay, okay.
Did you
show them once? So just show them, take the source once
Yeah,
again and place it and show asking them to press the escape button.
So once if you when you click on the any element, just click on the element and you will get direct element into the screen. So wherever you want, you can just click on there. So it will come like this. So after that, you have to press exit button. Once if you press exit button, then it will go, and then you can use this source wherever you want. Okay, but once if you keep the source, you can't rotate this. So further, you need to rotate before you keep the source. Okay, that is the main another important factor. So like that, for example, diode will take. Yeah, even we can get diode from here also. So then I have taken the diode. Just click on the right side of your mouse. Sorry. So if something comes like this, you can go for the Control Z options. So click on the right button. So when you click on the right button, so it will rotate. So you can place and exit. Yeah. Okay. Then after placing the elements, you can go here. You can see the wire option. So you can click on the wire option. So it will come to you. So wherever to whichever element if you want to connect, you can just connect directly by using this wire. That's it.
From where we are getting the wire option?
So everyone connected, right? So here you can see for your reference if you want to verify that. Yes, yes. Tell me. Yes, tell me, sir.
Hello, wire please look at the wire option where we are find.
Sorry, I couldn't hear you. Can you please tell me once again?
So wire option, wire option.
They're asking wire option, Vinay.
Okay, wire option. Yeah, fine. Wait. So here you in the above the screen, you can see a wire option. I have placed my cursor. Can you see?
Yes, sir. Yes, sir. Yes. Sir.
Yeah, below the Windows option. So there you will get the wire option. So yeah, you can click on that wire option, then you can connect. Okay, after connecting everything, you just need to press exit. Then only it will be diminished. Okay. Okay, hope everyone connected, right? So yeah, here I have made one design for example for a yeah, you can go for the note and show here. So everything is fine, right? So now we can place our elements here, so we can see. So we need to give the inputs. So here I have designed something buck converter. So where you can give the input is 24. Okay. Can you? Is it fine? Everything? Okay, then now you can go for the voltage source is 24 volt. So once if you placing the voltage source, then you can change the value name or else name if you need. Then after that, if you click on this, so you will get this value means value or name. So you will get on the simulation. So directly you will get, you can see here. So yeah, after that, just there is no need to save again. Just click on the close that block, then you will get everything. Automatically it will save. Okay. Then this is what 24 volt you got. We have given for this, and the next one here we need to get the voltage. Actually, this converter has made for the output voltage of 12. Okay, 12 volt. Okay, then we need to design the filter. So for that design, actually, I have taken the values like the output current is 20% of changing, means like delta L, means the change of the inductor current is 20% I have made. So with that I have calculated the L value. So the value is 1.25 millihenry. Okay, so you can enter here 1.25 milli directly. So the same thing, if you click here on the display and this value, so you will get it. So in this PCM, actually there is another advantage is that you don't need to keep a probes, okay, voltage probes or something, because here itself flags are available. Once if you click the once if you change the flag 0 to 1, then you will get output means expected element output. You can see directly on the simulation window. Okay, after the simulation. So just keep the current flag and the voltage flag 1. Okay, and 1.25 millihenry. So this is what our value. Okay. So the next value is the for the capacitor. So you can change capacitor name if you want, and you can click on the capacitance also. So the capacitance is actually in this actually capacitance is depends on the our change of the output voltage. So here I have considered change of the output voltage is 2% only. Okay, in the 12 volt, they have to take the 2% means 0.24% is the change of the 0.4 volt is the change of the output volt. So with that, I have calculated the capacitance. So the capacitance value which I got is 6.25 micro. For representing micro, you can directly just press U button, small u. Okay, don't keep it in capital. It is a small u. And after that, you can close. So here you can see the values. We'll zoom, little zoom, so you can see the value. Okay. So the next one is the load. So if you want to change the name as a load, you can change, then you can display the name, and the resistance we can keep for the 10 ohms. Okay, 10 ohms, and we can keep the current flag and the voltage flag is 1. Okay, and even for this we can keep a current flag is 1 and the voltage flag is 1. So now power part is over. Means the power circuit part we have given all the inputs. But the input voltage is 24 volt, and the inductance is 1.25 millihenry, and the capacitance is 6.25 microfarad, and the load is the 10 ohms resistance. Okay. Okay, everyone clear? If you have any doubt, you can chat. You can drop a message. So the next one is here you can see this part we have completed. This part we have completed, means the power circuit part. So the next part is control circuit part. Where it comes to the control, we know that we need to provide the duty ratio. Means the duty ratio means how much time it should be on the switch. Okay, comparing means the ratio of the turn on switch and the total time of switch. So that's what the duty ratio we need. And the next one is this is a V triangular. This triangular voltage means switching frequency. It means okay. So So this we need to construct there. Okay. So we'll construct. So we can take DC voltage here itself. So once if you place, you can click wherever you want, then press exit. And if for zooming option, we have zoom in, zoom out. And this is for this zoom box is a particular option where we want to zoom. Yes, you want to zoom when the circuit is more complex, you want to zoom see some particular point. Just example like this, only this point I want to zoom, then you can see. And this one, zoom to fit page. So this is for how much were the simulation circuit that everything it will fit into the single page. Okay. So after that, you can see here, you can see select option. Once if you click on the selection option, whatever you, because see the option zoom is still it is available for us in the cursor. So we need to leave that option. So when if you go for this select option, so everything will go. So now you will get a arrow cursor. So for everything it is fine. So yeah. So now we have got the DC source supply for giving even in the place of DC source, you can even give the constant block also. Okay, if you even you can give the constant block also, like a depends upon the how much voltage you are giving in the V triangular. Okay, so where if you go to the sources, so voltage sources, so where you can find the triangular waveform. Okay, so you can keep here. So we need the earthing. So you can find earthing here itself, ground. Okay. So we can keep ground for this circuit and as well as this and this. After that, you need to press exit button. So after we have taken the triangular waveform, and at the same time we have taken duty ratio. For duty ratio, we have taken DC source. Yes, yes.
హలో మేడం అది అప్పుడు మనం ఫిల్ చేసినప్పుడే అడిగాడు మేడం పేమెంట్.
Excuse me, ma'am. Can you please mute? Yeah. So here you can see in the comparator where you can here you can see the comparator. Okay. So you can use this comparator. So you can use this comparator. And the next one is this is very important. One of the important thing. This is
Hello?
actually switch on and off control. Hello.
Where is the symbol of comparator?
Yeah, you will get directly from here itself. The ground you can see library browser.
Okay.
So you will get directly from here. Okay. Can you see?
Okay, okay. Okay, yeah. Got it.
Yeah. Okay, fine. Or else if you want, you can go for a control box also. You can find comparator.
Okay.
Here. Okay, the next one is the wire option. So okay, sorry. First, another major important circuit is this on and off control switch. Okay, because this actually whatever here is the control. So for that we need to give this on and off switch. Then only switch will activate. Okay. So after that you can connect the circuit directly with you can give this and you can take the output. Okay, fine. So now we need to assign the values for this. So actually, we need 50% duty ratio for getting 24
No audio, sir. No audio. Hello. 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 Nothing is coming.
Sir, I can't hear you.
It is not. We can use this biomass to produce biofuel.
Sir, it is stuck, sir.
One second, I think it got struck. We are resolving.
Okay, sir. Thank you.
Okay, so thank you.
Offline.
Sir, your voice is not audible, sir.
I think Vinay is. I think he has some issue. So let me continue with that. Maybe I'll take this part, screen sharing part, and I'll do that. So one second. Can you see my screen? Hope you can able to see my screen now.
Yeah, we are unable to see your screen.
Now we can able to see. I think it is. I just started sharing.
Yes,
the screen.
sir. Yes.
Okay. Okay. So I think this is what Vinay started showing. Let me. I don't know what values he has kept, but so we took the DC source. So where we get it from like commonly used blocks. So from here you'll get it, and let me drag this. So I'm just showing everything what Vinay has shown. So up to here you are completed. So you can able to see. So I think all the blocks you have connected. So now we go for the control block. So where we took the reference value. So we can take the triangular wave. Yes. Tell me.
Can you explain the control circuit parameter values, sir?
Yes, yes, this part I'm showing. Yes, this entire part I'm showing. So up to here it was Vinay has showed you. So now we can. I'm just taking a comparator block for the generating of pulses, PWM pulses. So for generating of PWM pulses, we have to take reference with the sinusoidal wave or with the triangular wave. So I'm just taking this triangular wave with the duty cycle of 0.5 and frequency of 5 kilohertz, and we peak to peak voltage of 1 volt. So these are the things you have to take care. So once you enter these parameters, so I'm just keeping for some time. You can enter these parameters by tracking the triangular wave. The triangular wave signal you'll get it from elements, sources, and then voltage, and then the triangular. So directly you can take the triangular. So by default, it will be that peak to peak will be 2, and frequency will be 1000. Will be so just use this particular values. So just enter those values. And now we want to the reference signal. So the reference signal I'm taking as a DC source with the amplitude of 0.8. So I'm the reference versus the triangular waveform, sawtooth waveform. We can able to see the amplitude. Here we have given the 1, and here we are giving as 0.8. So that the PWM pulses will be available directly for you. So that pulses also we can able to check it by placing a voltage probe over here. So the voltage probe you'll get it from elements. So sorry, elements, other, and then probes. So we have two different voltage probes. One is differential and one is single-ended. So which the common ground. So here I took the common ground one, so single-ended one. So it will be like this. So once you are done, so just connect the circuit by wiring the option. So here you can see the difference from the power circuit and the control circuit. The power circuit will be the red color, so which you can see, and the control circuit will be the green color.
Excuse me, sir. Once again, can you please explain triangular waveform, triangular block?
Triangular waveform. Yes, triangular block. These are the parameters which I am giving. So this is the comparator block, which I'm giving out upper output level by default as 1 and lower output as 0. So that comparator block will get it from here. So directly you can drag and drop over here, and once you place it, press escape, and then you take a DC source So with amplitude of 0.8, and take a triangular source with the peak to peak as 1 volt and frequency of 5K. So if you want, you can increase the frequency and duty cycle also. We'll do slow one by one. So for the time being, you take the frequency of 5K and duty cycle of 0.5. So if you're not aware of the particular block, directly you can go to help option, which is already available in the particular option. Once you double click on the particular property, you'll have this offline help, sorry. So if you click on that, it will show you the parameters of that particular block, how they are designed. So what is the peak to peak and what is the frequency and how the units are designed. And if you are using triangular waveform, how it is illustrated and how the pulses will be displayed. So everything will be available. So I think it was okay. Now this part was completed,
sir,
right?
Excuse me, sir. Hello, sir.
Yes, ma'am.
Sir,
Yes,
in the diode FWD, how did that FWD form? Diode, yes, sir.
Okay, so if you want to enter the text file, so here we have an option called text. So just click on the text, and if whatever the thing you want, you can able to write over there, and you can increase the font. You can increase the font and press OK, and where you want to place it, you can able to place. So once you are done, the text will be available. So in wherever you want, you can able to press over there.
Thank you, sir.
So this is the option called text option. So now we have created this entire part. So now we'll give the signals to
pulses. Where we will get the pulses?
Okay. Basically, this is not a pulse. This is the voltage probe. So let me delete this. So for reference, maybe you're getting confused. Yeah, I think it is fine now. Correct. So this is voltage probe. This voltage probe will get it from here. So voltage probe, I'm placing a node to ground. So in order to verify my pulses. So in that, you can able to double click and you can change the parameter. You can able to give the voltage probe name also. I'm just giving as a pulses, and here you can able to enter display the name of the part also. So that's what I've done. I'm displaying that. So if you don't want, just delete it. As per your records, you can able to do. And once you enter all this part, now we have to give the pulses signals to my MOSFET switch, so to the switches. So in order to provide, so we can't able to give directly. So in between that, we should have a on-off switch controller where the trigger, the pulses will be on-off, and it will directly provide to the MOSFET. So for that, we should have a on-off switch. So it's not a diode, it's a on-off switch, on-off controller. So that on-off controller will get it from the here. So on-off switch controller. So so from the commonly used blocks, so after the gating block, you can able to see the on-off switch controller. So we have two options. One is gating block and one is on-off switch controller. I will explain you this. So now we'll use this on-off switch controller and give the signal to pulses part. Just connect the part to the pulses and the MOSFET. So parallel logic. So if something is there, just chat in the you can text in the chat window. I will able to see. Otherwise, you can unmute and you can talk to me. It's not a problem. One by one.
Excuse me, sir.
Yes.
Sir, that top left corner, one top signal is there.
Like, correct. I'll explain that. Correct. Once you have done this, let me know. So hope you have done this part. So now what I will do was this is the simulation control. So basically in MATLAB or any other softwares, so you have to enter the simulation control, right? So where the how much time the simulation has to run. So for this case, PWSIM has this separate block called simulation control. So that you'll get it from simulate and then simulation control. So just go to simulate and simulation control and place the block over there. Once you place the block, here we have the so simulation control is nothing but how much time you want to run the simulation with including the time step. So we have different options over here: time step, total time. So one major important thing which you have to consider was total time. So total time is nothing but how much time you want to run the simulation.
From?
So that part you'll get it from simulate and then simulation control. Go to simulate after the elements icon, and then simulate and then simulation control. Just drag and so once you click on that, you'll get a timing block. So place over in your circuit. Once you place it, you'll have this kind of simulation control setup by default. So if you're not giving the simulation control, PWSIM will run for 0.01 millisecond, 0.01 seconds. So which is 10 milliseconds. So by default, it will run for 10 milliseconds. But if you want for longer time, so you can run for 0.02 or 0.1 or 1 second also, and accordingly the simulation time will shown in the simulation window. That is called SimView window. So now I'm giving a total time as 0.02 and time step of 1 U. Okay, so here e power 005 is nothing but your microsecond. So the time step. So in detail, they have explained in that help option. So you can refer that also. So this is the time step which you are providing, and the time step ratio and total time, and the free run I'll explain you later. But for as important for now for this particular simulation was total time. So just give total time as 0.02. And here, so if you want to place a voltage probe, just place a voltage probe in the V0 also to refer the output. So as when I told earlier, so instead of giving the voltage not V0 also, we can able to get the waveforms across this particular load. So where we can able to give the voltage flag as 1 and current flag as 1. So this part I will explain you after seeing the results.
Yeah, I'm sorry, actually disconnected.
No issue. So like I'll explain this part also maybe for next circuit.
Yeah, yeah, you can continue. Yeah.
Okay. So now I'll run the simulation. So for running the simulation, you can go to simulate and then run simulation. So once you run the simulation, so you can see the total time taking for the simulation and what are the things you are provided in the circuit. So all those blocks will, all those properties will be available. So starts with the pulses. So we'll go with the pulses. So the pulses, you can see. So heat flow, it's not possible in this particular option. So that is available from the thermal module. I will maybe at the end of the session we'll show you that part also. So this is the so total time you can able to see 20 milliseconds, which we have given in the simulation control. So here we have different options. So if you want to zoom for that part for the particular option, we can able to select from the zooming option. So zoom box will be available. So where it will select a particular box and it will be zoomed. Okay. So here we have different options like auto scale y-axis. So y-axis will be scaled properly. So now we'll see the output of at the load side V output. So V0, which I place the probe. So this is my entire part. So because I have just zoomed this entire circuit, it is showing like this. So now I'll reload the data. So now we can able to see it starts with 80. Sorry, the voltage is rising at above 100 and it's settling at 80 degrees. So 80 volts. So this entire thing will be depends on how much pulses and how we are providing the pulse frequency part. So the same you can able to see that load current also. So which is IR1. So if you're not getting pulses, just see the circuit once, whether you have placed a probe or not. So which I placed a probe. So the probe will be available from here and place the probe and give the pulses. Name or V1 or just see what is the name you have, and once you are done, pulses you have to give the probe, and you have to see what name you have provided in the pulse in the particular probe. That probe you can able to verify over here. So here this entire probe options will be available. So for pulse part, I have given as a pulses in my probe. So that part you have to verify properly and you will get it. So just check once. So when entire thing you have provided the same or not. If not, let us know. Again, we'll show you. Not find simulation control block. The simulation control block, simulation. You can't find the simulation control block. Okay, so the simulation control block will be available from the simulate and then simulation control. Everything is provided as per your schematic, shall not getting pulses. So if you're not getting pulses, check whether it is connected properly or not. Here we have a bubble.
Maybe.
So if it is connected.
Maybe, yeah, maybe he have given something wrong in the triangular waveform or as triangular source or this, triangular source maybe.
Slide, okay, getting a.
Yeah, can you please check the triangular source DC offset value should be 0.
Yes, DC offset should be 0.
Values, yeah. Then you try.
So hope Nikhil is also provided the same. So just let us know if it is not working properly. So these are the parameters which you have to provide, and then once you are done, you can be able to get the schematic simulate window. So just go to the simulate. Okay, great.
Yeah, fine.
And now we can able to see the results over here. So in this, this is called simulate window. So what are the results you have placed? You can able to see over here. So if you want to measure the maximum value, minimum value, total hormone distortion, FFT analysis, all this can be done with a single click. So here we have an option called measure. So you can click on the maximum. So we'll get a maximum value. So you'll have a window called over here. In this window, you can able to see all the values. So for X1, X2, and delta average, RMS value, total hormone distortions. So directly everything will be available if you click on the measure option. So the measure option will be available from here also. Directly you can able to. So if you want to check between the 2 points, we have option. So here we are getting the horizontal lines. So this option will be available. So if you want to see the frequency or something, you can able to use this particular option. And one more important thing which we have was we can able to calculate the FFT analysis. So we can go to analysis and perform FFT analysis. Directly get the FFT analysis block. All these are the options available. So if you want to take the screenshot of the particular thing, instead of taking the screenshot, so I'll show you that part too. So for example, I want to present this part in my particular thesis or in projects. So here we can able to see a view, and we can go to edit and then select this copy to clipboard. View, edit, copy to clipboard, and you can select color bitmap. So now this entire schematic will be loaded, it's copied, and you can open a Word document and just place over there. So here you can see this entire schematic will be placed over here. So which is a good option instead of taking the snipping tool or other screenshot options. This option will help you out in presenting clear picture of your schematic. So like that, you can take the images, you can take the screen, you can copy the schematic results also, so waveform results. So just go to edit, copy to clipboard, and file bitmap or meta file format accordingly, and just you can able to see the results. So here directly you'll get the results, and you can able to zoom it also. So these are the options available directly from the PC. Clear? So if you want to do some mathematical equations, so that option is also available. So for example, if I want to calculate the power, so I have the V naught, I can multiply with I1, so which is the current, and I can see that I can able to add over here, and it will calculate and it will show you the power of your particular schematic. So we have different options. You can able to add or delete in the same.
Sir, can you please see the last step of multiplication? Sir, can you please show the last step multiplication?
Sure. So which I'm doing was so here I have the particular variables. These are the variables that I have available. So in order to calculate, so I'm just doing the power calculation. So for power calculations for the buck converter, what I'm doing was I'm calculating I naught into V naught. So I have a IR1, so which is the current. So just click on that and drop down over here. So just click on that and drop down from the window. So it will be shown in the window. And here we have a mathematical equations. So in this, I can able to take the multiplication, and I'm adding the V naught, and I'm dragging that. So now I got IR1 into V naught. So now this entire part I can able to add over here. So it is showing IR1 into V naught. So these are the options available. So once you click on over that, directly you'll get the power options. So here you can see IR1 into V naught.
Thank you, sir. Thank you.
So hope everyone will got the results. So these are the options. So if you want, you can save this particular file also. So you can go to save as. So by default, it will save as SimView document after running the schematic. If you save the schematic file, the SimView results also will be saved. If not, you can able to save as. The property options is nothing but directly once you click on the add one screen, you'll get the property window. Okay, so like this you can able to add. I got the server, so by now got.
Excuse me, sir.
Yes.
Hello.
Yes, tell me, sir.
Sir, the smoothness of your waveform is good, sir, but ours is getting too harmonic, sir.
Okay.
Your waveforms were like second order. Sorry, sir.
So, so this depends on what is the values you have provided. So let me show you the schematic once.
Capacitance I had provided one.
Sorry, sir.
Capacitance I provided 6.25 as said sir. Vinay sir.
Okay. Okay.
Okay, actually my design actually it is for 20 kilohertz, so everything is differ, sir. So that is the reason maybe.
If the pulses are varying, you can able to refer only this part. You can able to check the pulses. If it is output value, maybe the inductor value and the capacitor value what you are providing, it will vary on that.
Okay,
So
okay, okay, sir.
Just refer on this.
Pulses were getting, sir, and then waveforms all are getting, but the waveforms were differ from yours.
Because which I took for 100 volt.
Yeah.
So maybe the input which you have provided is will be 28.
I have taken for the 24 input voltage, and the output is 12 and the resistance is the 10 ohms like that. So one
Yes, sir.
20 kilohertz.
So these are the input values which you provided.
Okay, sir. I will change and then check, sir.
Yes. So someone has told we are getting some output controller because of this. So in this place, I think you have provided diode. So if you have, I'm showing the same error to you. So I'm just running the simulation. So hope you get the same error. The gate node of the switch should be connected to the switch or switch controller. So in this case, you have to place a on-off controller. So this on-off controller will be available from the down part. You can able to.
Sir, now I am getting, sir. Capacitor, if I change it, I am getting.
Okay.
Yeah.
Great.
Fine.
Okay.
Thank you, sir. Thank you so much.
So yes, from Sesi College, someone has replied this, so you can able to check that. I'm not sure who is that. Murthy sir. So you can able to see. Just place this on-off controller properly, and you'll get that start. So yes. So this is one circuit which I'm using on-off controller. So with the same instead of PWM pulses, how we are generating, I'm just deleting this entire part. You can save this particular circuit as a buck converter with PWM in operation. So one more thing we have was gating blocks. I'm just placing a gating block directly to my switch controllers, and I'm giving the by default as it is as it's a DC voltage, the frequency it's not a matter, and number of points which I'm giving for turning and turning of the switch. So I'm just for 1/2 cycle, I'm just turning at 0 and turning off at 180. So you can able to see the results now, the same results. So only the thing will not get the pulses, remaining everything will be the same. I'm not generating the pulses, I'm just generating the gating blocks. So this is called gating block. So for turning and turning of the switches. So for example, if you are working with inverter switching or converter switching, so where we'll have a step pulse. If you want to trigger at 30 degrees and switching off, turning off at 180 degrees. So in that case, it will help you out. So for inverters and the converters part, the rectifiers also it will work out. So for students, it will be very useful. What are the things you are practicing in the power electronics subject? So everything we can able to refer over here. So the demo version.
Sir, can you please?
Yes.
Sir, can you please show me the measure option in this tab? Measure option that was showing.
Come again. Measure. Okay. Measure. Okay. Measure option. So this measure is nothing but to calculate from maximum value, minimum value, next maximum, next minimum. So these are the options available. So if you click on the maximum, so if you click on the measure, you'll get all the values. What is the maximum value?
Sir,
what is
average RMS and total harmonic distortion. These are not coming.
If it's not coming, just go to analysis and just click on over here. So these are the by default and which I kept. And if you're not available, you can just click that.
Okay, sir. Okay, sir. Thank you.
And as it is a demo version, it will be available continuously. Yes, we'll show you that MATLAB Simlink also. So maybe I'll show you now. So after that, we can go for the next session, the next particular example, which when I will show you. So for example, if you want to take the MATLAB comparison, so in MATLAB, I'm just taking one particular switch. So this is the MOSFET which I'm having. So in MATLAB, as it is a mathematical representation, it is we can't enter the data sheet parameters. Okay, so where it is the ideal conditions. When in PWSIM, we can able to enter the level 2 characteristics of your switches also. So for example, if I'm doing a simulation, in order to get the measured value with the calculated results and with the practical results, so the ideal condition will work only with 75 to 80%, and the data sheet parameters will work to 90 to 95%. So that's how the simulation results will vary. And apart from that, the simulation time. So as it is designed only for power electronics, the simulation speed is very fast, which we can able to show you in a couple of simulations also. So for example, in the earlier session, so FOC of the induction motor, so it took only 2 or 3 seconds to run the entire simulation. So because the algorithm which we have used was KCL and KVL and tabular algorithm method, so that's why the simulation will be very fast. So these are the few points which I can able to tell you now. But apart from that, we have a couple of papers also which they have do the simulation comparison with MATLAB, SPICE, and PWSIM. So PWSIM will give the best and fast, accurate results. So apart from that, we can do the SPICE analysis also from the PWSIM. So that part also you can able to enter. So we can able to add the SPICE model. We have the different library directly. So PWSIM can do both control level simulation as well as the device level simulations. So these are the libraries available from the PSIM, and you can able to add that part also. Okay. So these are the few things I can able to tell you now. Yes. Yes. Tell me, sir. Tell me, sir.
I have a question. That you said that there are several parallel softwares like PSpice, then MATLAB and Multisim also be there. So what is the say for example I want to do some op-amp experiments, op-amp simulation. So we can do that in other software also. So what is the advantage over those softwares with this?
Sure, sir. As if you go to in the industry level, so they want to get the simulation in very faster time. So in that case, they will use data sheet parameters, everything. So in one software, they can able to utilize that. So in PSIM, we can do the control level simulation or system level simulation and device level simulation. Where Multisim, PSpice, LTSpice, all these are device level simulation, and MATLAB, LabVIEW, all these are control level simulation. In PSIM, we can do both. And we have the different modules where you can able to calculate the thermal characteristics or heat loss calculations. In PSpice or LTSpice, you can do the loss calculations. But here you can able to enter the datasheet datasheet parameters, and you can able to calculate the junction temperature, conduction losses, switching losses. All this can be calculated.
Okay, so another question that is this an open source software?
No, it's not an open source. It's not an open source. It's a paid one. We have a bundles kind of thing for academic point of view, where we can able to give different modules in one package with minimum pricing for number of users.
Okay, but right now I am using as from your link. So whether any other can do this?
Sorry.
I am using right now this software with link provided by you.
Correct. It's a demo version which we have provided. Yes, it's a demo version which we have provided. So it has some limitation, but you can able to, for basic learning purpose, you can able to utilize that software.
Yes, that's I am asking whether we can use with our students for lab experiments, all these things.
Yeah, basic experiments you can able to like buck converter, boost converter,
Yes.
some inverter level which you are showing now. So that everything you can able to do that.
Because it has, I think, a 555 timer module. I have seen that, and then op-amp module. So these modules are very, very popular in the lab experiment of our students. So I think this software is very helpful, and doing the project also. Final year projects, small projects. This simulation software can be very useful.
Correct, sir. Correct. Most of the universities have this software. So if your college need the particular software, let us know. We'll share you the quotation, and maybe further discussion we can able to discuss with our sales manager.
Okay, sir. Is there any manual type that you will provide? Can be provided manual?
Which one?
This for any manual. This software.
Manual. Okay. Correct. Manual will be available. So here you can go to help option, and we have few documents and the tutorials. And apart from that, see here we have so many tutorials, and PC manual will be directly available in the help option itself.
Sir, excuse me.
Apart from that, we have 100 plus video tutorials are available, so you can able to refer all those. Yes, ma'am.
Hello, sir. Excuse me. There is a MOSFET is there. So you are attached a triangular wave symbol like that. So where is the triangular wave, sir?
Triangular wave, you get it from so here you can able to see downside. These are the sources which we have available. So this is the DC source, sinusoidal, and the triangular wave.
Okay. Okay, sir. Thank you.
Yes, I think I've shown a couple of most. Now we'll go with the buck converter. So buck converter, I think you can able to just modify the same things. You can able to do by your own. If not, we'll show you that part also. Let me. Okay. So buck converter. So I'm just replacing the MOSFET and the inductor and the diode part. So you just drag and drop. So just select that and drag and drop, and once you're done, just place it over there. So which is very easy for you also. So I think buck converter, Vinay, can you show that for basic understanding? So you can be able to answer some other questions.
Sure. I will show.
I'll make you as a. I think you can. I'll make you as a presenter.
Yeah, fine.
Where are you? Yes, I got you.
Okay.
I'm looking as a presenter.
Yeah.
I'm making as a organized. Right. Yes. So right now we have gone through the buck converter. So now we can go to the boost. We are done. I mean, it's a simple one. We can be able to design as early as possible so that we can see the next options in the PC.
Okay, then we can go for the boost, right?
Yes, boost. We directly go to boost and show one basic example, and then go to parameter sweep and motor drive. So, and then we can go to power forge. So as the time which we have planned for 1:30. So if you want, we can go to extend if required. Otherwise, we can able to stop at 1:30 or 1:15. So, but we have to complete our agenda. So we are we'll start as early as possible. So we'll show you this entire.
Yeah. So this is what the boost converter design. So what are the elements we go for the buck converter? So the same elements are sufficient for our boost converter design also. Where you can see.
I think you can remove the file option. You can delete the file option.
Yes.
So,
okay, fine. Here you can see. But the placing of the elements, you can take care. Just you can see before the switch was here, but now the switch position was changed to here based upon the boost converter topology. So please change according to that. So yeah, even for the boost, we have made one design. So this design is for giving 12 volt to. I need to get output as a 10 volt, sorry, 24 volt. So what we done in the backup, so the reverse only we are doing here. So this input is the 12 volt. So whatever we gave here, the 12 volt. So yeah, so fine. We are getting here 12 volt. And the next one is the inductor value. So inductor value in the boost converter, it depends upon the input current also. Input current based upon the input current means the change in the inductor current, it depends on the input current. So that how we are calculating is from the input power that we are calculating the input current. So that actually I have taken that 10% as a change in the inductor current. So with that I have calculated the L value. So the final L value is 0.3125 milli. So here you can change the value to 0.3125 milli. Okay. So after keeping that, you can directly press exit. So the value is updated here. So the next one is the capacitor, the filter capacitor design. So the capacitor also is depends on the output voltage change, right? So I have already said that the same out with that I have calculated that capacitor value. So it is 50 microfarad. The change in the output is 2%. I have taken as a 2%. So that's what. So here you go. I got 50 micro. Make sure that it should be small u. Okay. And here you can change current flag. And here also, yeah, flags are updated. So this flag, yeah. And the next one is here the switching frequency what I have taken is 20 kilo. Okay. So 20 kilo. And the duty cycle is 0.5. Because for making 12 volt to 24 volt for the boost converter, so it requires a 0.5 duty ratio that I have shown in here. So yeah, then so here you can see because actually we have given the peak value is 1. So that's why we have given here the 50%. In that one, it is 50%, right? So 0.5. So this is what I have given. So make sure your design should be match this. So after that, we can go for the simulation. Once if you go simulate, 1 second, sorry. Actually, the load also, please change to 10 ohms. Okay, fine. Then you can go for the simulate option. Yeah. So where you can see the output resistance across the resistance, here you can take the both values. Sorry, I think something I have. Yeah, we can see here by keeping the probes whether our output is generating properly or not. So we can go for the simulation. So yeah. So this is what we are getting. Delete subsystem and try again. May I know which subsystem you are using? Actually, here in this part, there is no subsystem, right? Actually, in the demo version, we can't use the subsystem. There is a limitation in the demo version. So we can't use the subsystem in the demo version. So our pulses are generating properly. That is fine. So we can go. Just replace the position of components. Yeah, we will share the recording also, so you can go through that. Okay, fine. So over here we need to. Yeah. So have everyone got the output voltage? So here you can see the output voltage is I have said previously. So it is designed for the 24 volt. So here you can see the 24 volt output you are getting here. Yeah. So here you can see, and the change of the output voltage, as I said earlier, it is a change of output voltage is 0.48. So it's nearly half volt. So that's why from here to here it is changed. So here you can see. Okay, and next one we can add. Yeah, we can add the inductor current and also the capacitor current. So where you can see the inductor current and the capacitor current. So yeah, here you can see the inductor current and the capacitor current. Yeah, fine. So this is what, and the load current also, if you want, you can take and see just IR3. So this is what the load current we are getting. So 2.4 is the load current. Yeah, sure, sure, sir. So hope everyone is clear, right? So if any doubt recording this, you can ask. Yeah. So the next one, here we have designed everything the same, what Vishwanath told, that gating circuit where we can find here itself. So once if you, we can do with this
Nothing
also.
not required this anyway. Yes, yeah, not required. Just
Okay,
maybe can.
okay, fine.
So just
Yeah, yeah, sure.
maybe from this only you can able to show these parameters. So for this particular register value.
Yeah, that is better, I think. Yeah. So the parameter sweep we can do for this means, yeah, here you can go for the parameter. So where you can get here the parameter sweep. So if you take the parameter sweep and click on here and press exit, then after open the parameter sweep and where you want to do sweep, we need to first of all need to think. So example, I will try to do for the parameter sweep for this resistance. So that resistance. So for that, once we need to click on this to activate this cell. So after that, we need to give the name. Example is like a resistance R, and start value is like example.
One.
Yeah.
You can give one.
Yeah, one.
1 ohm to end of 10 ohm with increment of 2.
Yeah, with increment of 2. So this is what we can give. Then after, we need to come to the resistor and we need to change this name with whatever we name gave here in the parameter sheet. I have given is a R. For that, we need to take care and okay, finally we can run the simulation. So once if you run the simulation, so it will generate, normally it is 5 number, but it will generate with the 6 because it will take from the start and end and in between. So overall 6 will generate. So we can see how the output is varying when you change the resistance value from 0 to 10 ohm. So see here you can see when, oh wait, sorry. So here you can see with the when it is starting with means the condition 1 means which is 2 amp starting with the 1 ohm, after 2 ohm, 3 ohm, sorry, 4 ohm and 6 ohm, like that it will increase. So whenever you can see here and yeah. So and another one, here you can see how the resistance is varying. When you increase the resistance value 0, 2, 4, 6, 8, 12, so when it is increasing, so the voltage, how it is varying from 22 to 24, it is varying, depends upon the resistance. That's what we can find here. Hope everything is fine, right? So yeah. So this is what the parameter sweep. So you can, even for the capacitor, even for the inductor, also you can do this. Okay. So yeah. Whether everyone got right? Yeah. So we have completed buck converter and boost converter and parameter sweep. Yeah. So then final one is designing of the VSI inverter, right? Induction machine in the PWSIM. Okay. So for this actually we need, yeah, you can open new bar. So you can take it as a DC source from here itself. Once if you place the DC source, then IGBTs. Okay, so you can place the IGBTs according to the structure of the VSI inverter. So here you can see, you can follow with this also. So here you can see.
So where did you get the IGBTs from?
Yeah, you can get in the switches. Means where you can see whether you can directly go to the library and switch. You can get IGBT, or else you can get directly from the down. There will be library of essential things. So there also you will get IGBT. Okay, fine. Okay. The next one is that you need to connect this. So so I have connected everything. So the IGBT is according to my structure. So here you can see. So the next one, I need to take the ammeters to see the current. So you can directly go to the probes also, where you can see. Yeah, here you can see the probes. So voltage and current. So you can go for the current. You need 3 probes. So please keep the probes and connect with the wire. Okay, fine. Then after that, to sense the current, so after that, we need to take the induction motor, where you will get in the motor drive module. So you can go for the motor drive module, where you can see is here you can the motor drive module. So the first one you can take the induction motor. So you can connect here.
Hello, sir. Where you get that ammeter or AC source? A value.
Yeah, I understood that. You will get directly down the library. Can you see my screen?
Yeah, sir. Yeah, sir.
Yes. Or else you can get in the directly probes also. Okay. So that's what. So next we go. After connecting that, please go to. Okay. So we have connected the induction motor. So after connecting the induction motor, so you can go. So the next one is the speed sensor, and after that, constant torque load. So you can go for the sensors where you will get is a. So here you will get the sensors. You can, if you have any doubt, you can directly type here. So you will get everything. So directly you will get the speed sensor, and you can connect. And yeah. So where you will get is this sensor you can get in the here, and the next one is the probes. As if you ask, you can get in the voltage probe, current probe, everything here, and yeah. So after that, torque. So you can type here load itself. So you will get it directly. So but we need to take the constant torque load. Just take the constant torque load and keep there. Yeah, fine, everything. So yeah, After that, here you can see so the power circuit is completed as of requirement. So next we need to go for the control circuit. Okay, here I'm using the sine PWM. So where you are comparing the triangular pulse with the sine. Okay. You can take the sine source here itself. So yeah, you can connect. So the next one is after that we need to use the comparator to compare the sine values with the sawtooth. Yeah. So here itself you can take the comparator, just keep comparator. So after that, just connect these all with wire. So after that, we have to take the triangular waveform. So there you can get here itself directly. So if here and use the ground. And take the wire and connect. So you have they have connected everything. So here you can mention the peak value is 1. And the frequency you can mention at the 50. And here the phase angle you need to give, because we need to get the 3-phase waveform, right? So further 120 degrees. And here you need to give peak voltage is 1. Sorry, peak voltage is 2. And the DC offset is 1, -1. And 50 degrees. And the phase angle is 240. So please change here also 2 volt peak. And this offset is -1. Yeah. Just window. This offset is -1. Yeah. So now you can connect this to switches, where you can connect with on and off controls, where you can take from here itself. So we need to go two on the switch for the two switches. So you can keep here. And the next one is for giving, actually we need to operator. We need to operate these two switches in the opposite way. So for that we need to NAND gate. Then you will get the logic gates. So here in the logic elements you can get and not get. So where you can connect here for everything. So the next one, you can take the wire and just connect these two PPTs. Make sure that everything is perfect, because sometimes it may get interconnected. So make sure. So the next one. So here you can see the differences, like a green wire and here the red wire. So the green wire is for it represents the control action, and red wire it represents the power action. So it means the power level, and green wire is the control level. It means. So once if you connect, then coming to the parameters, here you can enter the 150 volt. So I will make it as so remaining parameters, whatever is there, actually this motor we can keep it as the default parameters. So we'll see, and we can give torque is 25 as Newton meter. So yeah, then we can use this voltage probe to see the speed. Okay, fine. So now we can run our simulation and we'll see whether everything is fine. We'll go for so where you will get that I1, I2, and I3. Sorry, because
So
actually
DC
I
voltage
have,
and triangular wave generator values.
yeah, here it is not DC actually, it is AC. We are actually
No, the
generating the
DC
sine.
one for the IGBT for the power.
No, it is actually inverter, right? So we are not giving the DC value. Here it is the sine value, okay? So here you can see the sine voltage. Okay. So here you can see.
So triangular wave generator frequency.
Yeah, I will. This frequency you can give as 1,000.
Excuse me, sir.
Yes, tell me.
The constant torque control before one device we are connected.
Yes, sir. This is actually for speed. This is
What
actually
the current
speed sensor, sir. Actually, to see the
sensors?
speed of the sensors. You can directly type in this find. You can directly type speed. You will get speed sensor.
Okay,
Or
sir.
you can
Thank you.
go through the or you can go to the elements and control, then you will get.
Okay, sir.
ఆశీర్వాద్ బాగుంటుంది అక్క. ఏనా ఉయ్యాల ఎవరున్నారు? తింటుందా? ఇంకన్నమ్మా
So where even you have the example here also, so directly you can see basically PWSIM. So yeah.
ఏనమ్మా ఉయ్యాల
So here you can see.
Sir, please mute the all participants. Sir, please mute all participants.
What I didn't get you. Okay, can you please whether everything is working? Just can you please show? So here you can see the duty offset value, everything.
Sir, what will be the simulation time in this case?
Simulation time, actually we can define that, is not a problem. 1 minute. So here actually 0.5 at the simulation time.
Okay.
And the step time is 10 to the power of -5.
Okay.
Yeah.
నీతో పాటు వచ్చి నీతో పాటు పోతుంది ఇంటికి వెళ్తున్నావని నాకు తెలుసులే. నీతో పాటు వచ్చి నీతో పాటు పోతుందిలే అనుకున్నాను. రేపు అట్లాగే నీతో పాటు వచ్చి నీతో పాటు.
Sir, please mute all participants.
Can you please go mute policing someone? Can you please? Yeah, fine. Excuse me, ma'am, Kamala ma'am. Can you please mute yourself? Yeah. So yeah. So I think hope everyone got right. Here you can see this is the values we have assigned. So this is for a 0 degree phase angle. So the 3-phase sine, so you will get directly. So the final output, you can hope everyone got this. Excuse me, ma'am, Kamala.
Hello, sir.
Tell me.
Sir, tell me how to connect that sensor block. Can you explain me once?
Yeah, sure. So you can actually, if you go to the library, so you can type the speed sensor. directly you will get the sensor, so that you can directly connect here itself. Okay.
Okay, sir.
Okay, fine.
చేయాలా
So this is actually torque. You can give the torque 40 constant torque.
Sorry, please mute the program.
Yes, yes. Excuse me, Kamala.
నేను పోయి చూసేటప్పుడు
Hello.
Yes, yes, yes.
Sir, can you tell me the load parameters?
Yes, yes. Here you can take the constant torque as the 40.
Okay.
Yeah, that is
Constant
enough. If you
torque as
want,
40.
yeah, if you want, you can enter some more parameters also. But here, for the example wise, we are actually just taking only constant torque.
Oh, I've taken a different component there. That is constant torque load, no? What is the component you've used?
Yes, yes, yes. Actually, there are even the torque, even the load sensor. You can see here. Here the constant power, constant torque, and the constant speed. There are many type of loads are there. You can.
It is only the maximum torque and base speed. Only this information is there.
Which one, sir?
Which one we have to take in this mechanical load?
Constant torque. Constant
Constant.
torque. Yes,
Okay.
yes.
Constant.
Excuse me, sir.
Yes, yes, yes. Tell me.
Sir, I'm getting error WSEN, that either mechanical interface block or a gearbox must be sent to the master. More like that, it is getting error. I think in the sensor.
Yeah, yeah. Whether which type, which sensor you used? Can you please tell?
Speed sensor only, sir.
Speed sensor WSN2, correct, right?
Yes, sir.
It is not connected properly to the motor and the load. So that is the error you are
Yes,
facing.
yes.
Okay, I will check.
Okay, can you please check once again, because it won't create any error, and which even see torque also.
I
Please
need
use
provide
the
the mechanical
mechanical
load. No, just
Okay.
remove that load once, Vinay. Just remove that and run the simulation now.
Okay.
We will get an error mostly. No, okay. So it is not connected properly in place.
Yes, some problem.
Yes, sir. Running, sir. Yes, sir.
Yeah.
Thank
you. Sir, in the gate pulse generation, why we are giving offset as -1?
Because actually we need to get actually it is a sine wave, right?
Okay.
So it will be the negative value will also will be there, right? So positive and negative. So that's why actually we are giving. Did you understand?
Okay. Normally, DC offset will change the level of the signal, no?
Yes, yes, yes. If you give offset as a 0, then all component, whatever the component you have shown, it means peak to peak is 2 volt, right? So that will be from 0 to 2 volt it will come. But when you give the offset is -1, so +1 to -1 it will come. But peak to peak is 2 volt.
Yes, Vinay, just show by making as DC offset 0 and show the pulses to them.
Yeah, yeah, sure. I will show. Yeah.
Basic understanding.
So
One place is enough. Yes. Now just see the name and
V6.
now run it. Yeah, V6.
V6.
And only place V6.
Yeah. So here you can see.
Yeah, it is -1 to 1. Because peak is 2 of 2. So this is 1. Now go to DC offset at 0.
-1 to +1. That's.
So make DC offset as 0.
Yes, yes. 1 minute. 1 minute.
Not required. Just leave it.
No, because actually, okay, fine. Then if the DC offset is 0,
No, it will PCM will take automatically. Yes.
So here we can go.
So it starts from
So
0
here you
if
can
your
see.
DC offset is 0.
Yeah. So the peak to peak is 2 volt. That's what it represents.
I think I think everyone
Yes.
I think okay with the
Sir,
PC software. So yes.
sir,
Yes. Yes.
sir, DC
Yes.
offset is, sir, DC offset is -1 for all the 3 cases.
Yes. Yes.
Yes, giving for the three
Actually,
common right?
here these cases actually you can use even three-phase sine wave also. But if you are when we are creating the residual, you can take that DC offset is the 0.9 and overall is the 2. Like that you can take. Okay.
Okay, sir. Sir, can we use parameter sweep for the load torque?
Actually, I don't.
Just open that the load torque
I
page.
will try. Yeah, that is. Yeah.
Where do I find that parameter sweep?
Just library browser, you can find the elements now. Otherwise, you can go to elements.
No,
Yeah.
actually, parameter sweep we can't do this. No, we
Go
can.
to elements.
No, generally for any circuit, how do we do this parametric sweep?
So basically, in order to calculate the right, for example, if you want to calculate the gain, so which gain is proper for your particular function, in that case, parameter sweep will help you a lot.
Okay, where it
How
is
to
available? Where I can find that? Where it is available?
You
Parametric
can find in the library. You can directly type the parameter, then you will get no problem to search. Or else you can even open for the yeah.
Not getting. Which tab that is there? Parametric sweep.
Yes, one.
So you can go to elements, other, and then at the end you'll have the parameters file.
Others. Okay, okay. Got it, sir. Thank you.
Okay.
Sir, I'm getting 0 current.
0 current. Which one actually? So
In simulation.
how much? Okay, whether this actually is. Can you please check the gate pulse whether a gate pulse is proper or not?
Yeah, the gate pulse is proper. I checked.
Okay, gate pulse is proper. So, but current is not coming.
Yes.
Whether you have placed the NOT gates.
Yes.
I'm getting all the voltages right, but not the current.
Voltages here, we are not placing any voltage, right?
Yeah.
You are showing any
No, all the
voltages
other.
Okay. So you are not whether any connection errors? Can you please check?
Oh yeah, sir. I'll check.
Yeah, because actually, if voltage is coming and what is the current should come right.
Sir, how to
Maybe
check
it was
the
short circuited. No,
dark
it was short circuited. Mostly it will make short circuited. So when you're connecting the ammeters to the three-phase source, right? So check whether only one point should be black. So the round part. So if it is short circuited, it will not get properly.
Yeah. I think we can move power force.
Yes,
Is it fine?
last 10 minutes. Yes, last 10 minutes we have. We can go to Power Forge. So just give the overview of the software and it will be fine. So if you want a
Yes.
further part, you can write us a mail to Vinay or to me, or if you want to have their quotations, you can write us a mail at sales@pwsim.com. For any software, directly can write us. Otherwise, we are giving our mail also for technical part. You can able to write us.
Sir, hello, sir.
Yes. Yes. Tell me.
Could you provide any material for this sessions and all, sir? Like manuals like that?
So manual help manual is there, sir. That PC manual, entire manual will be there with different modules. So PDF document is available. So it will be very
Not
useful
that one,
for
sir. Today, I mean, whatever be the sessions you are handled in others. For that,
we'll share you the PPT presentation. PPTs will share you.
okay, thank you, sir.
Okay, fine. Mammalian Islam, someone actually.
Yeah, I'm muted.
Yeah, fine. Then no problem.
So just
Okay.
start with Power Forge. If anything is there, they'll get back to us. So we'll see.
Okay, then we'll go to the Power Force. So I can show the.
I think we can show the PPT first, and which is more than enough for time being, and after that you can.
Yes. So we'll go to the. So I think everything is fine. So we'll go to the Power Force software. So this is the software is developed with the Power Design Technologies, France, and here. Yeah, it is the first computer aided software. So where you don't need to download the software in any system, just it is the web-based software for generating the report. Means design the converter and design the converters, means like a DC to DC converter or DC to three-phase AC converter. And not only the design, you can even compare with the different type of sweep analysis, like different types of PWM techniques, different types of means a different range of frequency sweep you can do, and different types of switches. If switching technology switches means a different type you can use, and you can find how it is working and all. So there is a lot of advantages. So I will show. So as I said earlier, so it is started in 2016 in France, Dallas, and overall 8 engineers plus scientists are working in the of course, and it is a spin-off company from the Laplace Laboratory and funded by the seed capital funds. And there are some innovation awards also got this software. So these actually power converters designs having the major challenges are like topology challenges and magnetics. Magnetic means the inductor or storage elements. That is the problem. And the next one is the thermal management is the other problem. And also the command means with the switching technology or something. So these are the main design challenges in the power converters. But with this powerful software, you can analysis very easily, and you can find which technologies are better suits to you. So that's what. Example one: if you any company, if you have engineer want to find which converter is suitable for their operation, at the same time which is suitable for their economic also. So there here it is like we need to calculate first of all data sheet parameters from the specification from the user. Then we need to calculate so many analysis part. Then after that we need to find the design elements, storage elements, and again the storage element design calculations and the testing. So everything again we'll see whether it is working or not. Then we'll do simulation. Again this process will be repeated for so many times with the different switches and different level of frequencies and that. But when it comes to the power forge, you don't need to bother much actually. You can directly view the specifications and you can choose some difference element in the library. Then you can generate a lot of iterative process, and finally you can take whichever the efficient viewers, maybe whether it is a more power density converter you need, or more efficient converter you need, or that everything you can select and you can choose, and you can download the a report format, and also you can directly import to the PWSIM software also. That is a feature also available for this software. Okay, so the next So these are the key features. Like there are two types of topologies are available: DC to DC and DC to AC, and it is a cloud-based software. And already there's the broad library also available, and automated design from the two-level to multi-level option also is there. So yeah. Also, this is actually designing of the three-phase DC SD converter. So I will show everything this in actually. So here you can see we can see one thing. DC differential mode filter, AC differential mode filter, and macro cells means switching modules, switch modules, and the cooling and the switch control. This all we'll do in this. Okay. So this is the way we will get compare the design process, where you can see here different types of switching technologies as SI, PWM, SVPWM, different types of frequency ranges, different types of switches like MOSFET, IGBT. So depends upon our application we can take here, and also these all the results will get mass, volume, cost, power loss, efficiency. So here you can compare everything, and we can draw the scatter plots for every application, and you can do the breakdown value plots also for the mass, like a AC side differential mode filter, DC side differential mode filter, cooling, macro cells, everything you can do. And finally, you can export the PSIM to PSIM file, or you can download the Excel report, whatever the inputs you gave, whatever the outputs you got, everything you can get. So this is what the web-based software. So it is very easy to access from anywhere, and very easy to work and design comparison for power converter. And multi-sweep analysis of the switching frequency and the semiconductor and switching topology is available. And yeah, multi-user calibrations is this. So we'll go to just I want to show one, just go how to cover the software. You can see. Yeah. So it is just a web-based software. That's why I'm opening in the Google Chrome. So you need just the email ID and the password after buying. So where you will get example here I can say DC to three-phase. This is a DC to three-phase circuit where you can give many parameters like. Thank you. So where you can see here, these are the parameters inputs you have to give, where the power means AC side power and DC side voltage and AC side voltage and the frequency of the output AC. And here you can see many topologies like a 2-level, 3-level, and multi-level SMC. So these are the types of topologies are available, and here you can see another one, the modulation strategy. Here you can see many types of modulation strategies are available, like a sine PWM, a space vector, multi-level space vector, and the DPWM. So these are the modulation strategies are available. So where here you can do the frequency sweep. Okay, from which frequency to which frequency you want to do that, you can do in the frequency. And here the difference of the switch. Example, one switch, if you here you can see it is a huge library. So depends upon your voltage rating, you can choose the switch current rating, and everything you can choose your own. And these are the 4 switch module technologies that are available here. So SiC MOSFET, SiC SA MOSFET, SIs, IGBT, and GNFET. So these are the available. So once if you select a reference switch, so and also thermal interface, also electrically insulated or else non-electrically insulated. That is also we need to mention. And one more advantage of the software is that you can get the overall cost of the converter by giving the individual cost, and by finally it will derive the how much cost it comes for the particular rating. So that is it will give, and for which part how much cost it can be, that is also it will give the report. So the next one is the cooling. Where it comes to the cooling, whether it is a resistance cooling or forced air cooling, that you need to mention. And also in this there are 2 types: auto design, and even auto design is there, and manual design is there. Here you can see resistance type and the forced heat sink type. And yeah, these are the parameters you need to mention, and the cost also. Okay, then next one is the differential filter, DC side differential mode filter, where you can use the C model capacitor model or off the shelf capacitor model, or here you can see C type filter or an LC type filter. That is also option available. So according to the requirement, we can choose the same as how we are giving in the DC side, same in the AC side also. So here you can select a different type of topologies for the AC side, where the L filter, delta connected filter, star connected LCR. So these are the different types are available. Once if you done everything, you can launch the design. When you launch the design, so finally it will come to here. Then, yeah. So finally, after launching the design, so you will get output here. So, yeah, here in the sweep history. So where you can see how many designs you have. See here, I have implemented 4 designs with the different frequencies, 3 design with the different technologies of switch. So that like that you can see, and you can see different types of frequency. That's what you can get. And in the benchmark result, you can see the scatter plot. Yeah, first of all, this is an important. So where you will get your design name, and same time you will get the mass, volume, cost, power, efficiency, and THD. And there are some parameters. Parameters are there, like here you can see specific power, power density, switching frequency, and module voltage rating. So these are, you can choose, depends upon requirement of application and everything. And even here you can draw the scatter plots, and it will give automatically maximum scatter plots. But if you want to draw your own scatter plot, you can draw with this selection of this. Okay, after some here I can take this as a somewhat best design for me. So I can open the design details where I can see everything. So yeah, where I can see everything. Where I can see the input and the output values. These are the output results. So further design, what is the mass of the full converter it will give? So here it is like a 1.03 kg, about 3 kgs. So and volume and power loss. So if you keep the cursor itself, it will show what is the value like that. And here you can see this is what we are actually generated. This is a differential mode filter, AC side differential mode filter, switching controller, and cooling, and macro cells. So here you can see the breakdown, means how much AC differential mode filter is occupying the mass and the full converter. So this is what, like this you can see the breakdown value. Yeah. So the breakdown values, and you can here you can see with the placement of the converter how it is placed. Yeah, and yeah, even the operating here you can see what are the inputs you have given, what are the outputs you got. That's what you will get. So for this design, the results of the DC current, DC side current, AC side current, DC side power. So these are THD, even temperature, even yeah. So switching controller. So this is what the results, modulation depth, and the next one is the macro cells. This is one of the important factor here, because you will get the power loss. See, power loss of the converter and the cost and the volume. So this is what you will get. So everything. So yeah. So these are the scatter. Comparison waveforms, how it is differ with another. So that's what. And it's a capacitor. Also, what are the inputs? What are the outputs? That also you will get to know. And here in the cooling, you can see what are the inputs you have given and what are the mass, volume, and cost, and power drop, how much. And here you can see the even the inductor design also it will give. So here you can see. So when it comes to the inductor design, also it will give the core, what is the core, what is the total core area, or what is the power of the winding. So everything it will give. So once if you that, so you can export this into the PSIM. So this file you can open in the PSIM software. So where you can get. So these are the, see here you can see the PSIM schematic. So you will get this full schematic. That's all. So that you can use in the PSIM software and you can work with that. And the capacitor also, you can see this is the way the capacitor they have arranged, and this is the output of the what is the cost. So everything, what is the means, even the series how to connect, means parallel connection, series connection also it will show. So this is the powerful software which will help very good at the primary stage, and to find the converter design, to find the power loss, efficiency, and cost of the converter. So these are the main factors you will get from this software. So hope everyone is clear. Yeah. If you have any doubts or queries, you can ask.
Hello. Hello, sir.
Yes, yes. Tell me, sir.
Hello.
Master. Yes, yes.
Yeah,
Tell me, sir.
this power force cannot be used for power systems. No?
No, sir. Actually,
No,
as
it's
of now,
only for power converter designing.
Yeah.
What I mean to say that so for any power system problem.
No, sir. Actually, this is mainly purely designed for the power electronics, means which is for AC to converters, and also two converters are available, like a DC to DC and DC to AC, three-phase AC. It's inverters and converters only we can develop in this, not for the power systems. Okay, thank you. Yeah, fine.
So if you want to do with power systems, you can use EMTP software, which we have done yesterday.
Yes. So there you can do full complete analysis for the power systems.
So okay, so thanks. So thanks everyone. If you have any queries, you can write us a mail to sales@pwsim.com or to g.vinay@pwsim.com or visnath.visnath.com. You can contact us, so you can able to go to our website, which pwsim.com, and you can find out further details. Please ask us for any queries. We'll be able to help you out. For sales part or technical part, you can able to contact us. So if you want further discussion on a particular software or based upon your requirement, you can have a one-to-one session Q2. So if you want to conduct some kind of sessions like this, we can able to organize at your college or online session also. We can able to do that. So thanks for the time. We'll catch up soon, maybe in other sessions. We have the webinar, so we can able to refer all those in our websites. So please in touch and be safe. So thanks, Vinay.
Yes.
Thanks for the session.
Yeah.
Thanks, everyone.
Yeah, thank you,
College and Satish Kumar.
Thank you all.
So we'll
for
share you the
joining the
presentations
session.
to the college, and Satish Kumar sir will provide to you as soon as possible.
Okay, thank you everyone
Thanks
for joining
everyone.
the
Ending the
session.
session. Thanks.
Yeah, we are going to end the session. Okay, bye. Thank you. Stay safe.
So
Afternoon session is there. Right?
Thanks. So
Afternoon session is there. Right? Satish. Hello, Satish. You have afternoon session, please.
No, I think today there is no other session, sir.
Okay.
Probably.
Thank you.